Hello, everyone. Can you guys hear me okay? Yeah. Are we on?
Yeah.
All right, good deal. Hello, everyone. My name is Bernadette Hernandez-Sanchez, and I'm with Sandia National Labs. Welcome to today's Marine Energy Composites and Manufacturing Workshop. We're excited for you to be here to share some of our information on different aspects of marine composites and the manufacturing ideas that are behind them. To kick off today's session, we'll be having a number of speakers. But before that, just want to go through some brief overviews of the WebEx features. Today, we will be having some breakout sessions that will automatically take place. There's also some features on polling. We'll go into more detail on those in a second. But this will be hopefully an interactive conference for you as well, so that way you can join us and giving us feedback on what you believe are some new directions for composites in manufacturing. So to kick us off, I just wanted to let everybody know that today's session is being recorded. And also, this is one of our last installments from the Composites in Manufacturing seminar series. If you missed our previous webinars, you can find them on the WPTO's R&D webinar series webpage, so a deep dive. And this session will also be recorded and prepared and presented on that webpage in about a week or two. So thank you for attending. Lauren, would you like to go ahead and kick us off?
Yeah, I'd be happy to, Bernie. Thanks.
Thank you.
So awesome. Good morning. So again, I'm Lauren Rudy. I'm a Marine Energy Technology Manager at DOE's Water Power Technologies Office. I'm excited to welcome you to today's workshop, as Bernie mentioned, culminating the last few weeks of webinars on composites for marine energy. So you should now be seeing the second slide showing the agenda for the first half of today. So the team at Sandia and PNNL, NREL, Montana State, and Florida Atlantic have done a great job of assembling a full and exciting agenda for today's workshop. So as you can see on the slide, you'll hear about industry-led manufacturing work and research focused on composites during the first portion of today's session. And then this will be followed by academic and national laboratory examples. And then moving into, for those of us on the East Coast, the afternoon portion of the agenda, you'll see that later in the workshop, speakers will then be covering reliability and its relationship to materials and manufacturing. So during the breakout sessions that you see identified from, again, in Eastern Time, 1 to 1:40 p.m., the WebEx will automatically divide guests into smaller groups. So look for that pop-up window on the WebEx. If you haven't participated in a WebEx breakout session before, WebEx will bring up a pop-up window and prompt you to enter and leave the session. So just to reiterate that your feedback during those breakout sessions is critical. We really want to learn and understand what the barriers are and what the opportunities are for composites and manufacturing in the space. And then if I go to the next slide. So during you may have seen on the previous slide that there will be a couple of 10-minute breaks during the course of today's workshop. So during those breaks, you'll see survey polling with a few questions. So maybe if somebody can put that link in the chat, so that way it's available for people to reference later. But you can either provide your answers either online using that link or texting if you're on a cell phone. I guess just a quick note, the cell phone option I believe only works with multiple choice, so not any short answer. So just a heads up on that. But regardless of which platform you use, note that all answers will be anonymous. And then, so moving to, I'll just give a quick overview of WPTO, and on this slide, our budget, for those who may not be familiar. So this year, we're already halfway through FY21. but our budget within the Water Power Technologies Office is $150 million, and of that, $109 million is set aside for marine energy. So a couple other things to point out that happened this fiscal year with our appropriations language is we also received new authorization language. So you may remember that we have been the Marine and Hydrokinetics Program. We are now officially the Marine Energy Program based on that new authorization language. And then Congress also expanded the definition of the research and development that we can fund within the marine energy space to also include pressure and salinity gradients. So those are just a couple of key points to highlight of changes from this fiscal year. So within the Marine Energy Program, the R&D that we fund is organized into 4 activity areas that you see shown on the slide here. Just wanted to point out that all of the work funded and all of the projects that are going on in the materials and manufacturing space fall within that foundational R&D activity area. So obviously, while communicating the impacts of that R&D is also an important piece, that is primarily where the actual R&D and those projects, reside. So then moving into the Powering the Blue Economy initiative, I did want to touch on this just briefly for those who may not be familiar. So our PBE, Powering the Blue Economy, or PBE initiative started a few years ago, and as you can see on the slide, there's lots of work going on in the space. So it's an exciting area in different markets where marine energy can provide unique solutions like wave-powered desal and the waves-to-water prize, or powering, ocean observing equipment and recharging unmanned vehicles. So potential area for investigation within the Powering the Blue Economy umbrella also includes markets like offshore aquaculture as well. So these are unique applications where marine energy, materials, and manufacturing systems can be key enablers to solving, some of the challenges in these spaces. And then, I lost my cursor there. There we go. And so you may have seen on the previous slide, I mentioned I had a call out for AMEC, which is the recently established Atlantic Marine Energy Center, which is focusing on PBE research. And that was selected from our FY20 funding opportunity announcement. But, just to reiterate that our office is still focusing on utility grid applications as well. So a few other foundational research projects selected from the same FOA focus on materials research, which you may be hearing more about later this morning, so I don't want to steal anyone's thunder. But just another point to call your attention to is that we also selected under that FOA is the Foundational Research Network Facilitator role, which that name is in flux, currently being updated. But through that role, the objective for POET, who was selected for that role, is to coordinate WPTO-funded research and really maximize the impact of the research carried out, across multiple institutions, as you see identified on the slide. So just a couple more slides before we dive into the really good stuff. But I did want to highlight the five priorities that are called out, long-term for our office. And you can see of the 3 that are focused for marine energy specifically, materials and manufacturing plays a role in all of those, right? So whether it's, reducing the cost for grid scale marine energy for a fully renewable grid, whether it's looking at, marine energy systems for climate resiliency and scientific opportunities in the ocean, or advancing water power and water systems for resiliency for remote communities and hard decarbonized applications. Materials and manufacturing systems are going to play, a key role in achieving all of those priorities. And so lastly, just a quick plug for our WaterWire and other ways to engage with the Water Power Technologies office. And with that, I think I'm at time. So I'll just, thank you again, and, hope we get some good engagement during the workshop today, and appreciate you being here. Bernie, back over to you.
Thank you, Lauren. So as we go ahead and transition to our next speaker, will be Paul Fabian from Composites Technology Development will be speaking to us next on his work in the advanced composites for marine energy. So we'll go ahead and get his slides up. Just double checking.
Can you hear me?
Can you hear me, Paul?
I can hear you. Can you hear
awesome.
me?
I can see you. Thank you. Go ahead. So Paul, I'll let you go ahead and get your slides connected.
Can you allow me to share the screen?
Yes.
You do have presenter privileges. You should be able to share your screen now.
Okay. Just have to find that.
There we go. We see it.
Awesome.
All right. Everything's up.
We do see your presenter view. So at I think up at the top you can do display settings and mirror.
Okay.
Or swap presenter view or duplicate. Yep. Yep. There you go.
Is that better?
Yes. Thank you.
All right.
Thank you, Paul.
All right. Thank you. I'm happy to be here this morning. I want to talk a little bit about advanced composites for marine energy that on a program that CTD has been working on together with Boyd Hydro and Penn State ARL. This work was primarily sponsored by DOE, so we'll move on. I was asked to just give a quick overview of what composite materials really are. And so I don't mean to insult anybody by getting too basic, but composites are really just two or more distinct materials that you put together, and in typical fashion, the materials have different physical properties, but by putting them together, you achieve greater performance advantage. And really, in the scope of what we're talking about here, you have two materials, typically a matrix or a resin. The resins can be, thermosets, thermoplastics. There's even metal matrix composites out there. And in addition, then you marry that matrix material with a reinforcement, and that's typically a fiber. It can be glass, carbon, Kevlar. Sometimes they're what they call continuous fibers, other times discontinuous. It can even be particulate that gets mixed into the resin, and that becomes a composite. But for today's discussion, what we're really talking about in advanced composites, typically that means carbon fiber and epoxy. And epoxy, there's a lot of different epoxy materials out there with different properties, but there's also other types of matrix materials like bismol-imide, cyanide esters, benzoxazine. So there's a wide variety of chemistries that can make up the resin or matrix in any composite. And so then the question is, why use composites? And there's lots of reasons, of course, but the primary one for most people where they start looking at composites is that you have a high strength to weight ratio. And as an example, carbon fiber composites can be 5 times stronger than your typical low carbon steel, but it weighs 1/5 of that steel. And so, you know, high modulus carbon fibers can have moduli, you know, above 100 MSI. So it really, you know, you can really tailor the material to what you're trying to do. Some of the other reasons, they're durable, meaning they can be corrosion resistant, withstand most environmental conditions, and they're definitely higher fracture toughness than a typical plastic that you see in use. They also allow greater design options. You can mold parts maybe easier than you can machining out of a metallic, and a lot of times you can mold to a near net shape with less finish work, less scrap. And because of that, you can often fabricate, you know, parts cheaper than similar metallic parts with less waste. So that's kind of just the primer on composites. This is an example, you know, this is a pretty, you know, amazing looking, the front end of a sports car, but you can see the whole thing is made out of a carbon fabric, carbon composite. There's different parts there. You know, these high-end sports cars, the big driver is for lightweight, but the other driver for a lot of these applications is just aesthetics, how it looks, you know, and it kind of goes to show high quality. It's kind of, you know, whether it really is or not is a different, you know, people can have different opinions, but it sends that message. So now let me transition over to the composite hydroturbine runner program. I'll use runner and blades interchangeably, so you know, if you hear me say blade, you'll know I'm talking about the runner. But this is a program that we entered into. It's been a couple of years since we started, but really the goal was to verify that composite materials could be economic and reliable alternative to traditional metallic runners that are used, with the idea being to reduce cost, you know, and increase energy capture. And so our objectives starting out was to prototype a weight-efficient, fatigue-resistant turbine runner blade using composite material to reduce mass and extend the service life. We also wanted to improve the reliability by developing a high-performance cavitation-resistant coating that would be put on the composite over the surface of the composite blade. And then we wanted to prove that out and get some real-world performance test data under true operating conditions. And so that's a lot of work to take off on, but today I'm just concentrating on the fabrication, the manufacturing of the composite runner blades. And so, but before you start manufacturing, you obviously have to design the part. You have to know that it's, or at least have a good idea that it's going to perform the way you want it to. And in this case, we did a lot of design. We looked at what were the driving requirements for the composite in operation. You know, and you look at stresses, strain, stiffness. You know, obviously anti-cavitation was a part of that. But the driving requirement structurally was the stiffness and deflection at the tip of the blade. And so after selecting the materials, which we selected a resin that CTD has developed and primarily for marine applications, and marrying that with the high modulus carbon fiber, then we did the design and did a lot of FEA to determine that it was going to perform. And so the sketch, the FEA analysis on the bottom left there shows on the left side that is a steel blade, and that's under operating conditions. I believe this is under max efficiency conditions. And the one on the right is the composite. And so we designed the composite to really mimic the deflections of the steel blade, you know, and so that we would have the same performance, or at least hopefully the same performance. And so you can see there that they are very similar, but we achieved that through a very complex set of design and the fiber layup within the part. And so you see in the top right there, we kind of divided the blade into 3 sections, and with each one with slightly different layup and different numbers of plies to get that same performance. And so that's a pretty involved process. It takes a while, but this was a high-end performance part, so you know it was worth the effort to make sure we got it right. And we did do testing, static testing on blades and stuff to make sure that we validated the analysis, but I'm not going to get into that here. So moving on into the actual manufacturing, and the big step here is deciding which process to use. You know, and there's a lot of different methods of fabricating a composite. Liquid resin infusion, pre-preg vacuum bag, that's the primary process that aerospace uses. But there's also what they call vacuum-assisted resin transfer molding, or VARDM, and that was the process that we selected. And what that means is you are using either a 1- or 2-part mold, depending on what surface finish you need and stuff. You might only need one side that has a controlled surface. In some cases, like for us, we wanted both surfaces controlled, so we used a 2-part mold. But in this process, you have a dry fiber preform that you place inside the mold. You degas or evacuate all the air from that dry preform. And when I say dry preform, I'm talking about lots of layers stacked up on top of each other. And so you can see down in the lower left, there's, in some cases, we had over 100 plies of fiber stacked up to get the proper thickness and get the properties where we wanted it. But once you degas that and get all the air out, then you inject resin in there. The resin is degassed to make sure you don't have entrained air in the resin, and then that's injected into the mold and the resin impregnates and wets the fiber. Once it's fully wetted, then you cure the part. And so this just shows the dry fiber preform. Just for reference, these blades are nominally about 18 inches across in the longest section and probably about 14 inches deep across the height of the blade. Down here in the root section, the thickness is a little bit over inch, and that comes down to about a 1/4 inch thick at the tips. And so the layup and actually all the plies and making sure that you get the right fiber volume fraction within the part and maintain the thickness, that's you know, that's involved and takes a lot of engineering to do that, but it's certainly not beyond the capabilities of most places. And so then the lower right photo shows the dry fiber preform inside the mold. That's 1/2 of the mold there, and you see that there's a silicone rubber gasket that goes around the blade, and that maintains the vacuum seal when we do the impregnation. So then moving on, you know, once you close up the mold, you have to, you know, plummet. And in this case, we have 3 different resin inlets, usually located on the bottom. So you have a resin inlet line that comes down to a manifold. And then you also have vacuum and or resin exit ports that come out. This is where you're actively pulling vacuum, in this case to degas the dry fiber preform. And you can see this is a composite tool. This was a prototype, so we weren't, you know, looking at long-term production here, so we went with a cheaper option to and fabricated the mold out of a carbon fiber composite itself. And you can see the outline of the blade here, and you can see where the resin inlets are below the blade, the resin exit ports are above the blade inside there. So, and of course, in this case, the resin we're using is an elevated temperature processing resin. So this is all done inside of a vacuum that you can heat up. In this case, we were impregnating at 80°C. And so these are just a couple more pictures. This shows the blade, the mold, after the resin has traveled through the tubing. This is high temperature Teflon tubing, and then the resin has come out of the mold. And then on the right-hand side, you see after the cure, we remove the top part. So this is what the blade looks like after you pull it out. And so you see that you have the resin flash around the outer surfaces or outer edges of the blade. You can see these are the lower impregnation or resin inlet ports. And up here you can see the 3 resin outlet vacuum ports to the mold. Following that, we have, in this case, we did some post-fabrication machining. So the resin flash was taken off, but we had some very high tolerance dimensions that we needed to make on the lower edges of the blade. And so that was actually done with the CNC machining. And so, but you can see these are all of those fiber plies and now have become a solid composites. We have very low void content. We matched the fiber volume fraction that we wanted in these cases. But you can see how the thickness changes from the root area here, but out to the edges becomes quite thin. So just like a typical hydroturbine blade that you would machine from a metallic, this was molded to that shape. And then the next process that we had to go through was actually bonding the composite blade to a metallic hub. And this process was fairly simple in the composite industry, but we were using an aerospace grade structural adhesive. And so we did some initial sanding to get the right fit into this hub, and then we had to make sure we were maintaining the correct bond line thickness. So these are just some shims that we know the thickness, and the idea was to keep a 7/1000th of an inch bond line thickness between the metallic and the composite. And so here you see, we've applied the adhesive. The adhesive was also applied into the metallic, and it's being placed in there. There's some tricks that you use to make sure that you maintain that bond line thickness, but really nothing major. You will see here, you should notice here that there are 2 holes. We also match drilled the part once it was bonded and put 2 pins through here just as a safety measure, just to make sure that we had sufficient margin. and make sure we didn't have anything catastrophic happen once we were actually testing. We did do a lot of FEA and analysis on the bond line, make sure it could withstand the stresses and that we were going to place on it. So, and so this is really the finished bonded blade with the hub insert. This metallic hub, we used that because this was going to interface into Penn State's ARLs, their hydroturbine in their water tunnel that we're also designing, a simulated hydroturbine. And so we weren't sure exactly how they were going to interface, and so it was thought best to make this part out of metallic. But, you know, of course, I think you could make that out of composites if, you know, you knew the exact hub interface and could design that. And so then the last step really was to apply this cavitation-resistant coating. In this case, we were using one of our products called CTD-133. That's actually a pre-preg resin system, but we did a lot of testing in the first year looking at coatings and did a lot of erosion, cavitation, erosion in the water tunnel at ARL, as well as other tests, and did a lot of different materials. One of the leading materials was actually EPDM rubber, but we found when we put it in the water tunnel that we could never achieve a good enough bond of that rubber to the composite that would allow the rubber to stay bonded and take that cavitation. But with the 133 resin coating on there, we found that it was very resistant to cavitation and extended the operation time by years if you extrapolated time. So that's what we went with. And so you see that has been coated. The little piece up there is just a composite, carbon composite witness sample that we put up there just to show the color change. So in conclusion here, you know, really all I want to say is we did fabricate some very high quality composite runners. We used the Bardem process as well as other processes that are typical in a composite fabrication job. In this case, the polymer coating at the end is something that maybe it isn't typical, but a lot of times you are painting or putting some coating on for protection. We did do static and fatigue tests on this that showed that the composite parts behaved as well or better than the typical 410 stainless steel that's used for these runners. And we talked about the cavitation coating providing longer use time. And the big thing here is these runners are, compared to the typical solid stainless steel runners, these parts are greater than 50% less than the all steel blades. So just handling them, changing out blades is going to save a lot of time and effort on everybody's part. And then we did fabricate a set of these 3 runners that we're awaiting testing currently at Penn State ARL in their 48-inch water tunnel. Below the photo or sketch below actually shows the simulated hydroturbine that we have designed and fabricated parts. It's being currently being inserted into their water tunnel right now, and then our blades will mount onto the simulated turbine, and then we're going to run a lot of different tests: max power, max efficiency, controlled runaway, uncontrolled runaway, different operating conditions. And I do want to say, I did forget to mention that, you know, the design of this blade was taken from a design that Boyd Hydro provided to us. And so it's an actual, we did scale it down to about 78% of its actual size to fit inside the water tunnel, but everything else, you know, all the contours and everything remain the same as the blade that the VoIP Hydro currently uses. So that is all I have.
Thank you, Paul.
Any questions?
Okay, we have time for maybe one question. Feel free to put it into the chat box. While we're waiting for a question, let's go ahead and get the next presenter's slides up. Carla, go ahead and start adding your slides. So Paul, how long did this take you, or how long was your project to get to where you showed?
Well, really, to get to from the first year was really focused on looking at coatings and developing those anti-cavitation coatings. The second year is when we started the design, and probably from the start of the design to the first part was probably about 6 to 7 months. A lot of that was, you know, fabricating tooling, getting fiber ordered, and in this case we had to use some very high modulus Mitsubishi fiber that is not off the shelf, so that took a little bit to get into play. You know, but really not that long if you think about what we were trying to do.
Thank you, Paul. Okay, let's see, our next presenter is Carla Simoni. Carla, would you go ahead and, oops, we lost your slides.
And I can't unmute myself. Are you guys able to hear me?
I can, yes.
Okay, I'm trying to find my video button too, and I'm not seeing the option on my video, so I apologize. Here we go, I found it. It was smooth, guys. I had the PowerPoint up, we were ready to go, and then I lost my video. Okay, I am here now. And we've got the slide deck up, excellent. Well, good morning. So Paul did a great job going into some of the composite manufacturing of parts. With Janicki Industries, we are a large-scale advanced composite parts and tooling company. I am sure a lot of you are familiar with us, so I apologize if some of this is something you've seen before, a little redundant, but just really want to based on also a good spin-off of what Paul just got done discussing, the selection of the tooling and molds and your different opportunities for starting off some of your projects. So like Bernadette said, I'm Carla Simoni. I'm with Janicki Industries. I've been there for about 3 years now. I am a sales engineer for the team. I also do have Jed Bridge available as well on the call. And so with that, for those that aren't maybe extremely familiar with us, we are located up in Cedar Woolley, Washington. It's about an hour north of Seattle. We do have, we're still a privately owned company with over 800 employees. We are rapidly still hiring engineers to support all of our different projects. And as you can see, the space that we have available to execute different tooling and parts projects. Like I said, we started pretty grassroots with one CNC mill that we thought we were going to sell. That's kind of how the company got started. Peter Janicki thought he was going to be selling these 5-axis mills. Found out nobody wanted to buy them, but they would love if we could make their parts for them or their tooling for them. And as you can see, over the years, we've definitely advanced into several different industries, which have allowed us to learn about all the different advanced composite materials and exotic metals that you can use from everything from aerospace and space to renewable energy, and still holding on to the marine roots. So marine renewable energy is right up our, we'll just say, the things that we love to do. We have worked really hard on diversifying our value chain business areas so we can start helping out early on in your program. We love to get involved when you're still trying to select materials or trying to understand what temperatures, how can we, help with the design for manufacturability. And then we are expanding even our research and development to help with testing out some of those choices. And then obviously once you are ready to start fabricating, creating the tooling, whether it's just prototype tooling to test out your new project, or once you're ready to go into full production mode. We do help out with parts, especially with prototyping parts or low run parts. You're just trying to get a feel for it. You don't want to set up your own manufacturing facility, or you just honestly don't want to learn how to make the composite parts. You want to focus on the engineering and the development of your program, but you would like someone else to take care of the composites. And then with that, also assembling of that final product. Just a quick, like I said, that mill 1 is still the original mill that we put into production in '93. And from there, we have developed 10 more mills with super accuracy. So once we get, get into the tooling that I could go through, you can get cast tooling if you're just looking for the shape and some of the basic function. We could still get that cast tooling to plus or minus 60. Or if we need to then post machine either your tooling or your parts, we can get these pretty accurate. So kind of along the theme of marine energy and development, a lot of these low rate layup molds are a good fit if you're just trying to get off the ground and get something into the water. We have our standard putty molds. As you can see here, we could do pretty, up in that upper left corner, we could do some pretty basic shapes, all the way down to, as you can see down below, a pretty exotic boat shape there. And then also for some slightly higher temp materials, we machine pretty accurate tooling board. What you see in the right there is a fiberglass with a steel substructure. And then down below is most likely one of our 360 CMs, which is a higher temp carbon fiber mold that is post-machined. It gets pretty highly accurate, and it's good for, like I said, those either prototype autoclave parts that you might need, or a few more runs of an out of autoclave, but with a higher temp. So these are a great option to get that very complex geometry that you can only really pull off with composites, and then still produce the parts that you need for a cost-effective price. Kind of going into that too, another secondary good option are these kind of medium rate layup molds. These are, most of these can also operate at a slightly higher temperature. It does reduce, there's the trade-off that you get to decide if you want, if you need that higher temperature, or if you're also using it to maybe get, like those previous ones, you can get like 1 to 10 good parts off of them. There's some refurb work on those putty patterns to keep that, the integrity that they need. But these, we could definitely also do increased cycles. So this is a really good fit. For example, you can see in there that the wind blade down there, it's a prototype type wind blade master. So when it allows our customers to then, you don't need usually just one wind blade or one rotor blade or one, So it allows you to get, you know, several, obviously that's a pressure side or suction side. It's too hard to tell from the inverse there in that picture, but it allows you to get enough components off of it to run either a low rate test on several different, or, you know, for example, like a wind blade where you would need 3 or 4 blades anyways. And again, kind of just in these pictures, these are more either a hybrid of fiberglass and carbon, or looking like some straight carbon here. And then once you've proven what you need, or if there's something that you need for super high temp, we do have our high rate production. This is when you're ready to get going. And so I won't spend too much time on this today, but just know that, you know, we have developed these for very high temperatures and very high rates. So just quickly kind of going through that tooling, especially on that, you saw that on that medium rate screen there. Let me just see, I have a little laser pointer here, down here with the finish. So this is just kind of the process to go through this. It's pretty unique if you haven't seen it before. So I like to show this slide. It just gives you an idea of, you know, when we give you a lead time of, you know, when you're wanting your tooling, just to kind of see what it goes through to get to this final product. So we actually, that putty pattern is kind of our first step as a good cast source tool. This can be used, and I'm looking at, here we go, sorry. This final finish here, this could be used as a one-off mold for your part if you're needing it. It's low temp here. It does have vacuum integrity, but it can also be used as a source mold for a higher rate tool as well. So just kind of going through this, we start in our buck shop that we, with our carpenters, and then it goes in and gets a foam spray that gets rough milled into somewhat a very rough net geometry, where then we apply our proprietary putty onto this, or fiberglass it, and then apply our putty on there that is a very good machinable putty. Go through that final milling stage with that putty to get it to that net geometry, and then we can finish this off. We can fog Duratec this and take it up to 400 grit, or we can even take it higher. Or the next option is we could just take it right back into mold fabrication, and this is where we would lay up a face sheet on the completed putty pattern, do a vacuum infusion process through there to get your final face sheet, and then we actually bond the substructure onto the mold while it's still in that putty pattern. And then once it's demolded from this final, you know, it's got a final cure and everything like that, we do have the option of going back in, like I said, and milling these molds to a much higher tolerance. So depending on your needs, we can just do this cast, or it can go back into our 5-axis mill and get you to this final product here. And kill my laser here. So with that, those are kind of our main product line opportunities for you for when you're looking at advancing your projects to that low rate production and or prototype tooling. So I just wanted to go through some of the projects pretty quickly here. I don't want to go over, get us too far behind schedule here. So with the wind energy tooling, just one of those things where I know we're focusing on marine renewable, but I do have to say the processes transfer pretty well. Like I said, we've done both carbon fiber and fiberglass components. As you look at the wind energy industry, mostly fiberglass, here's a nice large scale mold with an assembly fixture that we designed to actually then fabricate the full blade. And you can see here some of the full blades that we have completed. Not going to stick on that too much. I think everybody's pretty comfortable with the wind energy industry. And then this is a really good example. We participated in the Oracle racing boat fabrication. This is a great example of our quick moving prototype type of activity with a marine application, of course, but we did help them, you know, this obviously would not consider this a prototype, but an actual, you know, just a one-off racing boat, but we fabricated a lot, or they were able to fabricate a lot of their parts off of our rapid putty patterns. So there's that there. And then this is just an example of, you know, how large you can go. You know, this is a large hull for what you can see of that yacht down there in the bottom right corner. I always like this picture because of how tiny that guy looks hanging out in that hull. And then this is just another example of our kind of low rate production parts. This is a 24, 22 meter fish tank. It's compiled of about 104 different fiberglass parts. And we actually did make those all in-house. So we did make all that layup tooling required, which there are a lot of these parts that are like there's 16 of them. So you have one mold that can make 16 of these. And then we have to have a different geometry mold to make the next 16 and so on and so forth. And then to also make these, the fins here that you see on the left, you know, that was a different mold to create those. But this is a really good example of a project that, you know, they had this idea. They actually wanted to use the fish tanks themselves. They didn't want to manufacture these. So we did all the tooling and the parts for this project. These fish tanks have been up in the lake for, I think, over 6 years now, still fully functional. Just a great application for fiberglass. It allowed for flex with the waves, you know, working on that laminate schedule for that fiberglass for the flexing and the wear and tear that they see by being in the water all the time. So just a great application of composites. And then, and I guess with that, I didn't have a ton of other projects to go through, but again, I just, you know, you can just do so much with composites, as you're well aware, in all these different industries, with all these different materials. And so with that, I guess if there's any questions.
So on the agri-marine, the big hull that you kind of showed for this fish, you know, to take care of the fish, did that take, you know, was that an easy feature to kind of assemble all those different areas, or was that kind of difficult to try to, you know, put this all together to be this one modular shape that's connected?
That's a good question. So we did ship all of these components up separately, and as you can see, it was assembled on site. Okay. And Jed, who, there's a reason I told Jed to go ahead and hop on and be a panelist with me. Jed actually had an opportunity to go up there and see these, and I believe the assembly wasn't terrible. I mean, these were all engineered to fit together. And so I think the construction of the overall tank went okay.
Yeah, the original concept was to ship these in a shipping container around the world, and they actually did ship some to Norway as well. And so, yeah, they're quite modular and fairly easy to erect, probably about, you know, a week or so to bolt these all together and launch them.
Nice. Thank you.
Carla, this is Bill Peter from Oak Ridge. I had a question. With some of the putty as well as composite methodologies, are you using subtractive or are you also looking at additive methodologies to make some of those tools?
As far as additive manufacturing, I guess we can't say we aren't looking at it. I don't know if there's a tooling company anymore who's not looking at it. We are still focused on what we do best. But again, not saying that Jed actually even has to talk to this, but we do have a good research and development lab, and they're always making sure that we are doing the right thing for our customers, and if it's the right time and when it's time to get into it. As of right now, all of our standard is still the traditional tooling, but yeah, like I said, we can't say we're not looking into it.
Right. Thank you, Carla.
Thanks.
Absolutely.
Okay, so we'll go ahead and thank you, Carla, for presenting this. This is really awesome information, and it's so cool to see all these different parts come together in the particular process. So we're going to go ahead and get ready to take a break, and during our break, we'll start our polling session. In the chat, there was a little link for you guys to go to another website, and it'll help, and you guys could be interactive. And the first question, Francisco will help lead us on.
I assume we can only pick one. Bernie,
Yes, that is,
okay, thank you.
that is correct.
Hello, Ryan. Are the poll numbers coming through?
Hey, Bernie, I'm not seeing any responses come through.
Oh, huh, interesting. Well, maybe we could try that one again in the next round. Let's go ahead and start proceeding with our panel discussion. George, would you like to go ahead and lead us off in the panel?
Sure. Can you hear me, Bernie?
Yes.
Okay, let me turn my camera on too. So hello, everybody. For panel discussion today, we have 3 speakers, each of whom will introduce themselves with a slide and a brief discussion about who they are and what they do. So to start off, I'd like to introduce Matthew Barrington from Ocean Renewable Power Company, or ORPC. Matthew, are you on?
Hey, good morning, guys. So Bernie, can you share this slide I shared with you yesterday, or Ryan? Oh, I have to present myself. Hey, Bernie, do you have it handy, or do you want me to share it?
Go ahead, Matt.
We didn't practice this yesterday. Let me see if I can find.
So for the audience, while we're pulling this up, we would invite you to submit any questions that you have into the chat box, and we'll present those, but we do have a few questions in the can, as it were, that we'll ask our panelists as well.
Cool, thanks, George. I guess you can see my screen now. Sorry about that. I feel very untechnological. So yeah, I'm Matty Barrington from ORPC. I'm a mechanical engineer focused on the development of our turbines. Over the years, ORPC have developed turbines for ocean current, tidal, and river turbines. Today we're going to focus the conversation on our RivGen turbine. It's currently operating in Alaska in the village of Igiagig. So traditionally we use traditional tooling. We machine a plug, pull a tool off the plug, then use traditional carbon prepreg to make our hydrofoils. You can see the image in the bottom left, some boat builders building our current set of turbines. Our turbines consist of 3 hydrofoils connected with E-glass struts to a steel shaft. The shaft has welded flanges that the struts are bolted to. And our foils are connected to the struts with a mechanical fastener, a mechanical joint. I've looked at many joints over the years, and sort of through different R&D efforts, settled on a mechanical joint. So some highlights for the company, or for the RivGen project in particular. We've been deployed for 18 consecutive months. That's included 2 winter operations. The turbines have rotated over 15 million times. This gives us really valuable data for developing the next generation of turbines. We've observed no negative effects to the environment, to the fish that the village rely on. And yeah, like I said, we've operated through 2 pretty harsh Alaska winters. The image in the top right there, you can see our turbine spinning happily underneath ice during the ice out in the springtime. So yeah, I'm glad to be here. If there's any questions, I look forward to trying to answer them. Thank you.
Thank you, Matthew. Our second panelist today is Professor Iwana Jasuk, and I apologize if I mispronounced the name, but Professor, if you wouldn't mind introducing yourself.
Yes, hello. Hello, everyone. Can you hear me? Can you see me? All right. So I think, Professor Leo Chamorro has the slides, so we have sent you the slides. So I don't know if you could load it or. Leo could load it. But anyway, I can start with introduce myself. So I am Ivona Jasiuk. I'm professor in mechanical science and engineering department at the University of Illinois at Urbana-Champaign. I do hold affiliate appointments in aerospace engineering and civil and environmental engineering. My interests are in NTS. And also, I have been a site director of the NSF Industry University Cooperative Research Center for novel high voltage temperature materials and structures. The focus of this center was on novel materials for power transfer and for aerospace. Regarding my interests, I am interested in structure property, or I've been working on structure property relations in materials, employing micromechanics tools, design of new materials, characterizing and modeling, and using traditional manufacturing approaches, and recently embracing additive manufacturing because of flexibility to address new architectures, new microstructures of materials. Regarding specific examples of materials, definitely composite materials with a big focus on interfaces in composites, effects of interfaces in composites, high temperature polymers, which relates to the project that we'll outline. And and also looking at bio-inspiration, so studying biological materials and looking for ideas from nature to create new high-performance materials, and also high interest in sustainable materials.
Thank you. Sorry.
And and my colleague, Leonardo Chamorro, is also participating in this panel, so maybe he could introduce himself, and then we could outline the project that we are working on.
Okay, yes. Hello, thank you, Ivona. Hello, everyone. Very quick. I'm associate professor at the Department of Mechanical Science and Engineering at the University of Illinois Urbana-Champaign. And then I look the complementary problems, which is related to the wind and marine energy and tightly related to the material and composite, which is what is the effect, what we should consider for the unsteady multi-scale flow structure interaction. And then I also look closely into the hydrodynamics, aerodynamics, turbulence aspect of the wind and marine energy, and also try to perform advanced flow diagnostics to assess, to improve, to optimize design of material composite with Ivona. And then here it will show our project that we will start soon here. So Ivona?
Yes, sure. So yes, the project is new blade materials for marine energy converters, the converters operating in highly turbulent currents. So our objective is to engineer, test, and optimize the material systems. I'm not sure if I can show, I'm not sure if my cursor is showing, but the three-layered systems are shown in the left bottom corner. So our idea was to, first of all, we are using a novel polymer, which I'll mention about in a moment. But also we want, so that one idea will be to fully employ this novel polymer and its composites, and then also in a separate case combine it with wood as a layered sandwich system. And third plate will involve also steel, the composite, and wood. So basically, we want to study contribution of different types of materials and the blade properties. And we chose wood because of many of its advantages, and also because it's a biological material, and we plan to treat it in a certain way to optimize its properties. And then we wanted to also, for comparison, include some steel addition to make it closer to past designs. So the materials are novel polymers, more specifically vitrimers, and we refer to them as aromatic thermosetting copolyesters. For short, we call them ATSP. So these are high glass transition, low moisture uptake vitrimers. So vitrimers are thermosets, but they behave, so they have all the advantages of thermosets as far as good high cross-linking and excellent mechanical properties, but they also have characteristics of thermoplastics, meaning that they can be recycled and remolded. So ATSP will be used in this project as a matrix for the composites that we'll be using. Can also be in the form of a foam, as well as it has excellent bonding characteristics, so will be used as adhesive for these laminated structures. And and we showed the ATSP, because of its vitrimer characteristic, it has a property of exhibits bond exchange reactions. So under heat, it can glue itself to itself or to other materials, which make seamless interfaces. And regarding the design, so we'll be using, of course, as a start, what has been done in industry, but or in this area, but also combine it with modeling such as topology optimization and machine learning, but also include bioinspiration. I've been studying a number of biological materials which exhibit lightweight, impact resistance, high strength. So we'll be using layering, sandwich-like structures, porosity, and other interfaces and other phenomena found in biological materials, and use these ideas to create high-performance polymers for this polymer composites and composite layered systems for this project.
Thank you,
Leo.
Oh, we do just real quick. We do have a question in the chat, and this one was directed to Matthew, and it asks, did you use anything specific to seal your composites to prevent water ingress over long periods of time?
Great question. That question comes up quite often when we're developing turbines. We did some studies in the past, actually, in 2018 with David Miller, looking at water uptake in composites. Gave us some pretty valuable information. I think the outcome of that was you can slow down the ingress of water, but you cannot stop water getting into your composite. So is it valuable to slow it down, or do you just let it in and deal with the mechanical property degradation that you would see? So there's no specific coding to hinder the water going into our composites that are currently in operation, which are something we will continue to look at, though.
Thank you. Another question for the entire group, and perhaps I'll direct this one first to Professor Chamorro, but would like each of you to answer this, and that is, how is working with composites different from working with alloys, metal alloys, I'm assuming there? Professor Chamorro?
Hello, can you hear me? Maybe I can follow Iguana. Iguana, maybe you can jump in first.
Okay.
Sure. Yeah, so this is a very broad and very general question. Yeah. So how is it different? Of course, it's very different, but the goals are the same to create new materials, optimize properties for different characteristics of a material. I think composites have been around for a long time, since 1960s or earlier, and going back, they've been used thousands of years ago, with a classical example of clay and straw to create housing. So it's very different, but both fields are well established and require different types of expertise. But I've been working in both areas actually. Yeah, both open new challenges. But I am more excited or interested intellectually in composites because they open many more possibilities as far as working with different architectures, microstructures, employing interfaces, and combining materials to create new materials. So I don't know if I answered the question well. It's a very, very complex question with requiring either a very simple answer or very, very long and complex answer.
Definitely very open. Matt, perhaps you could comment from your perspective, or Matthew, sorry, your perspective from ORPC.
Yeah, sure. Yeah, so maybe a more practical, the two main areas that come to mind is in the initial design stage, when you're looking at composites, is the orthotropic material properties you have to deal with. It requires a lot more attention to detail, coming up with the layup schedule, a lot of finite element analysis required to look at the strains and how the stresses propagate around the leading edge of the foil and how the joint interfaces. So there's a lot more work up front. And then practically when you're building composite parts, you can't just buy stock steel and cut it and weld it. You have to build the tooling and make the part essentially to its net shape. So there's a different manufacturing steps than there would be with standard mechanical alloy and material.
Yeah, and analysis is certainly very complex because of all the different interfaces and architectures and anisotropy and yeah.
Well, like you were saying, they're very capable. You can do a lot with composites once you get into them.
Actually, we do have another question directed to the Illinois team, and that is, what type of fiber will be used in the ASTP matrix?
So one can use, most of the research involving ATSP composites, based composites, has been on carbon fibers and carbon-based nano fillers. So ATSP has great affinity to carbon, but it can be also used with glass fibers or basalt fibers or other fibers.
Okay. Let's see, another question, again for Matthew. What was your experience in manufacturing using composites to build RivGen?
Okay, sort of similar to the previous question. RivGen in particular, there was quite a lot of design effort to build a turbine that will last. Like I said, it's been operating consecutively for 18 months. 15 million cycles. This is a really high cycle fatigue machine. It's really hard to analyze up front how this device will perform over the years. So then coming up with the layup and how to make a foil stiff enough. This foil has cantilevered ends, so we're looking at how the foil will perform as it's sort of deflecting in the flow. So there was a lot of computational fluid dynamic analysis, a lot of FEA analysis, and we worked closely with the manufacturer who had an in-house design team to finalize the design. So it was a collaborative effort in that regard.
there another comment? Let's see. Another, this is again a fairly open-ended question, but what are the drawbacks of using composites? Maybe we'll pitch that back over to Illinois first.
Okay, so I think the main drawback is complexity.
Pardon?
As discussed before. But they open lots of opportunities. And one can see it in various industries. Initially, aerospace was very hesitant to use composites, and now it has embraced it, and similarly other industries. So it requires, because of all the complexity, interfaces, mismatched properties, residual stresses, the analysis is quite complex at microstructural level to obtain, to have predictive tools for failure in such materials. So I would say these are the drawbacks, but with all the equipment and characterization techniques that have been developed, and computational power that is available, these can be overcome.
I guess I can jump in here, speaking more practically from ORPC's point of view. The upfront design work is one thing, but also quickly iterating through different parts is not really feasible. The length of time it takes to build the tooling, and then the cost associated with that tooling, sort of sets you into a design for a certain period of time. So if you could quickly iterate through different tools, so maybe when additive manufacturing becomes more readily available, it might open up more opportunities to quickly iterate through designs and get more efficient turbines out there.
Another question we have from the audience. Oh, sorry.
Yeah, and another, of course, limitation may be temperature, right? That they cannot, obviously metals or ceramics generally can be used for higher temperature applications. But high temperature polymers are sufficient for most technological applications.
We have another question from the audience, and that is, what is the projected cost compared to existing resin systems for the ASTP matrix?
Good question. So this is a new, relatively new material with small volumes being created now, but the material, the ingredients are comparable to. I mean, the cost of ingredients or the components is not as comparable to the existing, but it's a combination of expertise and so on. So actually, this project is in collaboration with a small company, ATSP Innovations, and they commercialize these materials. So I do not want to, make a statement, but it's the prices are competitive and are explored for and these materials are explored for aerospace, space, and now marine energy composites and other applications.
Okay. So another question for Matthew. For a new company that's getting started, how many prototypes or iterations were actually needed before you got to a deployable system?
That's a great question. So I've been with ORPC for a little while, but back, I guess, 14 years ago, when they were just starting out, I know there's some offcuts of foils in the office, and there's a foil that's made of wood. It's like a wood core with glass fiber wrapped around it. And I think from there, then there was some different plastic tooling and some carbon glass hybrid foils. There's been many iterations of different turbines for different tests throughout the years. And so I can't give a definitive answer, but it takes taken a long time to get to where we are now, where we can operate continuously for multiple years. That answers your question. It's kind of a vague answer, but
definitely challenge. And then we have this is another very broad question, certainly very hot topic these days, but for the entire panel, do you think that composites can be made in a sustainable fashion?
The answer is yes. So that question can be, one can look at this question from different viewpoints. So one is making them in a sustainable way, but of course also using the components that are sustainable. So one, of course, one desired requirement for such materials would be recyclability. But there is also high potential in using waste polymers, breaking them down into monomers and then combining into new polymers. So it's a great opportunity for creating new polymers or making making existing ones, but using virgin monomers. So the idea is, so general, if it's just like remelted, the properties will not be as good as of original material. But if one uses, one depolymerizes it into monomers, then one can start from scratch and achieve comparable materials. So there is, there's high interest in upscaling of polymers, and I think it's a great field or a great opportunity for using such materials for high-end applications.
Yeah, and I could just really quickly add too that our subsidiary ORPC Ireland over in Europe have just started a project looking at using recycled carbon fiber to build our turbine. And so we'll see over the next couple of years if these materials are able to withstand the environment we put them in. But it is a very exciting area to start looking at reusability of our materials.
Question here for Leonardo. How do fluid structure interactions affect composites and their manufacturing?
Yes, this is a very, very relevant question, highly tied with the technology. We have to consider the materials, the composite, the systems that they operate in a very highly complex environment, and then this distinct behavior between wind and marine environment. And even in marine environment, we have different conditions, force and steady force conditions that we have to account in the design, the effect of persistent and not persistent, let's say, force, pressure, velocity fluctuations that we have to move to adapt the new composite and material system to adapt to their particular needs in particular environments. So there is here is a completely opening area that needs a lot of R&D and industry help.
And I think this will be our last question. This one is for Matthew again. ORPC has been working in both riverine and ocean environments. Is there a different approach in material selection for the two environments?
Great question. With the steel structure, we use a cathodic protection system, and that system would differ between a freshwater and a saltwater environment. As for the composites in the turbine, the same material set will be used in both. And you could probably start looking at different coatings for different environments. If one environment has more sediment, you might need to put a wear-resistant coating on our turbines. But for now, yeah, we're using the same system for both environments. Good question, though. Thank you.
Okay, thank you. I think we've run out of time. I would encourage the audience, if you do have further questions, you can put those in the chat and direct those to the panelists. But at this point, thank you, everybody. It's a little awkward virtually. We can't applaud, but virtual applause. And I will turn this back over to Bernie for our next speaker.
Great, thank you very much.
Thank you, everybody.
Thank you, George. That was great information from the panelists. Our next presenter is William Bill Keeter, who's the Director of Manufacturing and Demonstration at Oak Ridge National Laboratory. Bill, are you able to share your slides? Perfect, they're coming up. All right, I'll let you take it away. Thank you.
Wonderful. Everybody can hear me too? I'm not on mute?
I can hear you.
Wonderful. Thank you very much. Well, I really appreciate both Lauren and Bernie. Thank you very much for the invite to present today. I'm going to talk for the next 15 minutes about the various technologies that we have at the MDF at Oak Ridge National Laboratory that are allowing us to look at rapid fabrication of energy systems. And of course, as I go through, I'll try to catch on specific areas that I think have impact within the marine area. We have performed several different projects within water power, but I think there's a large space within marine that we could also be helping people with. To get started, one of the things that has recently been shaped within Oak Ridge is we just started a new directorate that's the Energy Science and Technology Directorate that's really looking at integrated energy systems and how do we take manufacturing along with these energy systems and start to pull them together to think much differently about how we enable new manufacturing technologies and low cost or affordable approaches to different forms of renewable energy, as well as infrastructure. This is an example on the infrastructure side. Buildings, actually the picture that you see in the background is of the Domino Sugar Building. It's in New York. If you go by this, I think it's a 40-story building. All the outside facade is precast concrete that was pulled off of 3D printed carbon fiber reinforced tools. And we did this with gate construction. First 40 molds were fabricated here. We then transferred the technology in a company called AES up in Akron, Ohio, went through and fabricated the rest of the molds. Instead of taking 5 to 10 pulls off of a given mold through conventional hand-built tools, you could get up to 100 pulls off of a given mold, and we don't know where it'll stop. That was just where we stopped pulling off of these tools. But it gives you a great idea of not just thinking small as we get into these areas, but how do we get into large systems, and composite printing in large scale is something that Oak Ridge has spent a lot of time and developed a lot of technologies out of it. Today, Oak Ridge is looking at essentially 6 different areas in manufacturing: additive manufacturing, carbon fiber composites, machining, roll-to-roll type process like battery fabrication, thermal process intensification, and digital metalworks. Across the board, we're thinking about digital manufacturing, artificial intelligence. How do we actually use some of these new concepts and computation to help us as we're going through and look at security, the information that we pull from the systems, and really automate and get to the right rates of production as we try to look at different applications. I'm not going to be talking a lot about that, but that's in the background as we talk a lot about a lot of these areas. I will be talking quite a bit in additive and composites, and you're also going to see where our machining capabilities really helped us to finish out these both molds as well as composite components. The manufacturing demonstration facility is sponsored by the Advanced Manufacturing Office. We started in 2012. The whole idea was to create a place where advanced manufacturing technologies were being developed and that industry could come in, leverage what was being developed inside the facility, and even be able to go through and perform projects with us. And so we have our core research and development where we're heavily connected with the machining manufacturers. We have over 100 different systems in our facility. I'm only going to get into a very skinny portion of discussion within those systems. Most of those are actually put here at no cost to us. It's part of the cost share by the partner. In fact, 60% of our equipment is in that scenario. So we're really trying to help transform what we're seeing in the technologies get them off the floor, get them commercialized, and help industry. And so one of the mechanisms we have to do that is every year we have funds that are put to the side called industry collaborations, and a funding or announcement, a broad announcement where a company that comes in and sees what we're doing can talk to us and work with us on putting a proposal together. And within a couple of weeks, we review it, and if DOE gives us the green light, we can go through and actually work on projects with companies. And you'll see that we've had over 200 different projects in that area, about 20 to 40 new projects each year. No money changes hands. It's essentially DOE funding us to work with that company, and the company doing an in-kind cost share of equivalently what DOE is spending. Like I said, this has been highly successful. I am not going to spend much time in powder bed systems today, and I'm actually not going to spend a lot of time in the machining. Where I'm going to spend the most of my time is in the composites area. I will talk a little bit about large-scale metal as well as it pertains to some of the composite activities. There are over 100 people inside the facility. We also do a lot of internships. We've had over 1,000 internships since our inception. One of the technologies that I wanted to bring up was large-scale deposition of steels, Invar, and other alloys, especially as we get into things like Invar and in the case of steel, the ideas for what we can do with composites as we start forming up these really large components. One of the big areas for us is tooling, and the United States lost about 37% of the die and tool industry in less than a decade. We're looking at new ways that you can bring those areas back and continue to develop upon those. And this idea of just-in-time or being able to go through and become very agile with rapid fabrication and local ability to fabricate your own tools and/or repair your tools is a big area that we're spending a lot of time with. We've done a lot of work in steel. We've actually done a couple different projects in Invar. Invar is important because of the low coefficient of thermal expansion, so that if we want to start looking at putting it into a furnace and not having distortion of your tool, you can go through and do so. But perfect example of this is the component you see in the bottom. This is a B-pillar tool, a steel tool that we actually produced, and then it went on to a major vehicle line in which they started producing the B-pillars off of it, hot forming metal. I'll be showing you some composite components that came off tools here in just a few minutes to give you an idea. This happens to be Medusa. It is a 3 MIG welder, so we have an arc with a wire feed, and we're developing the system to make really large tools where these arms work in tandem and help to go through and create these parts. So how do you go about doing this at high production rates into really large parts? Another area that we're developing, and I'm not going to spend a lot of time on this, but I think it's important as we talk about marine energy, as well as look at different other forms of hydropower, is concrete printing. This is SkyBAM. This is a system in which we really wanted to come up with a rugged system where you could deploy it very quickly and make it whatever size you want. And so this additive printer essentially is a fully based system. You have 4 base units, and then you have a middle point or fulcrum that basically holds the deposition head. And from that, I can make it whatever size you want and set it up within 30 to 60 minutes. Here you're talking about tonnage per hour, not poundage per hour. So we're able to go about a ton per hour in the current way that we're depositing it. And I've started printing out really large infrastructure-sized componentry using this. Of course, the SkyBAM, it could also be a pulley system, could be used for metals as well as polymers as we start going into really large systems. But all the controls in this system were all developed in-house, and something that's exciting to go to really big parts. I'm going to switch gears now and go heavy into the composites area in our research. For years and years, well over 60, Oak Ridge National Laboratory has heavily been into composite research. You have both the carbon fiber technology facility. I'll be talking quite a bit about that, where we're looking at new fiber production. The MDF, where we're going through and looking at composites manufacturing. You also have our chemistry department that has polymer recycling, who's spending a lot of time in developing next generation polymers and looking at recyclable polymers. And then we also have composite laboratories and carbon laboratories on the main campus. To close it out, even though for the most part in these sessions we've been talking about polymeric composites, we also have a high temperature composite manufacturing space where we've also been doing a lot of work in things like SiC or carbon-carbon type composites as well. When you start looking at the breadth of capability we have, and this is really where everything under one roof to help companies in looking at the research side of this. We've got everything from, as I talked about, the carbon fiber processing, including the ability to melt spin precursors if we want to go into some new fiber production of new materials. The thermoplastic and thermoset composite equipment, characterization, molding capability, additive manufacturing, which you'll see we have quite a bit and really help develop this entire industry. And then recycling and recovery is an area that we've spent more and more time in as well, with capability to go through, not just look at first production, but how we make sure that we utilize the value within these materials as we produce them. And that's an area that is spending more time in. One of the things that's behind all this is looking at sustainable practices. We're also looking at the idea of bio-derived materials, working with University of Maine, which is spoke to the MDF, and have been looking at large-scale printing of cellulosic materials and taking advantage of some of the structural scenarios in compositing with those bio-derived materials. The CFTF is a 25-ton per year facility for producing carbon fiber. It's the length of a football field, essentially what you would expect if you went to a fiber production facility. It's the only one in the United States where you can really go through and perform research and develop new precursors. The whole idea is trying to see, can we get into low-cost fiber development that will allow us to start using carbon fiber in more applications. I've already talked about at the front end the melt spinning capability. We also have sizing capability on the back end so that we can go through and prepare the fiber for where we use it, as well as chopping, winding capability all inside that facility. In the additive space, we've spent a lot of time developing systems, and it's at all ranges of systems. Whether you come in and we use a small-scale commercial system like some of our Stratasys systems, to some of our homegrown systems over the years, like the blue gantry you see here, to then working with partners. And there's about 7 different companies that use the extruder technology that we've worked with partners like Strong Press across the board inside these areas. We've got a lot of capability here and continue to push what we can do within these printers. One of the areas that I want to bring up, and I've got a component right here, this is foam. Not only are we going through and looking at reinforced materials, but we can also go through and look at foaming of these materials and getting different densities. One of our Cincinnati van printers actually can co-extrude 2 different materials. And so from a marine side, if I want to change buoyancy or density at point-specific locations, I can go through and tailor the properties as we go through and lay out the material. This is going to be important as we also talk about some of the composite work where we can automate and go directly from deposition to then high rates of production within composite fabrication. So really creating hybrid opportunities to link conventional techniques with additive or some of these newly developed techniques as we go through. There's quite a bit of mention as we talk about tooling and some of the previous talks as well, and where that means for what we're doing in composite fabrication. Some of the different areas as we do this. This is a perfect example of a hood that was VARTEM produced component where we were able to produce the tool within a couple hours, machine it, and then be able to start producing parts. So the idea is to be able to rapidly start fabricating this. In this case, it was a thermoplastic that we did the VARTEM with. But it gives you a really good idea of how you can, within a couple days, start producing new prototype components. And that's something from an agility standpoint in the U.S. and how that deploys new energy systems, we're spending a lot of time in development. We're also doing thermoset printing, and so where a lot of these thermoplastics, you may have very anisotropic property sets and directional functionality. We are also doing thermoset printing where you can get much more uniform property sets and get good bonding between those layers. The MVP Thermobot that you see there is a perfect example of that. We've also worked hand in hand with Ingersoll. They've produced a system that's up at Maine, as I talked about, one of our partners today, that's about 25 feet by 60 feet by about 10 feet tall. So giving you some idea of how big and scale these systems are getting. Then we have a lot of composites equipment, and this is right in the bay next to where we're doing our additive printing. So you can imagine the fact that I print a tool rapidly and then can start pulling it over into our composites equipment and then start producing composite parts off of that. Everything from thermoforming to injection molding, compression molding. Here's a perfect example of a component where by 3D printing we can point specifically change the chemistry and the orientation of fiber as we put it down. And then very rapidly after going through and depositing it, automate it, bring it over, put it into a compression mold machine and stamp it out. Now this is flat. A lot of the activities that we're doing are looking at three-dimensional components, but this shows you the idea of being able to go through and 3D print and then compression mold parts. So being able to take advantage of hybrid type techniques. One of the things I'll point out that's getting in here as well is out-of-plane printing. So getting into robotic systems as we start printing as well. IACME, we were a founding member of IACME. It's right next door to us. A lot of the composites equipment that I talked about, quite a bit of it is owned by IACME. Between UT, the forming ecosystem that we have in East Tennessee, and IACME, it's really created a great synergy of being able to do composite work here within the MDF. If we don't have the system, we develop systems and spend a lot of time in figuring out new functionality, automation, controls. This is just a small segment of the various different systems that we help co-develop. Typically, that's done with an equipment manufacturer that then goes through and creates a commercial system after we're finished. The big impact, though, is how this affects the various energy-related industries that we see. And I've got several different examples from hydro, wind, nuclear, buildings, transportation, fossil, that give just some sense of the scale and the types of things that we've developed. Everything from direct fabrication to the tools I talked about to also rapid prototyping. One example that I want to go through and show, and I know I don't have enough time to play the video of Emily, but is in a scenario for a low-head hydro. We were looking at the idea of putting, helping her with airfoils. Originally, we looked at 3D printing of casting molds that were then aluminum cast, which you see in this picture. That enabled her to go over and test 10 systems out at NREL in Golden, Colorado. And from that, was able to go through it and actually make a major deal with GE, now fabricate these systems that are very rugged and are put in very different man-made reservoirs. By doing this approach, we reduced the cost by 80% and allowed her to be able to even do this testing. Both the hydrofoils as well as a gearbox, we looked at this approach. Now we're actually going through and going back and showing the fabrication of composite hydrofoils that will enable them to go to larger lengths within those hydrofoils. So very excited to start looking at a longer term production that would have huge huge benefits in performance. And that is one project of a whole bunch. Like I said, we've had over 200, and obviously would love to sit down and talk further about other activities and things we've done or interests you may have. The other thing I wanted to mention was that Water Power also has a current program out called TEAMER, Testing Expertise for Marine Energy. Oak Ridge is one of those, as well as the MDF. And so whether or not it makes sense under the Tech Collaboration Program, which is led by the Advanced Manufacturing Office, or Water Power, there may be an opportunity for us to go through and help you in looking at your solution. And with that, I will stop. Bernie and everyone, you're still there, right? I'm not disconnected.
Can you hear me?
Yeah, I can now.
Okay, sorry, I was muted again. We do have a question from you. It says, awesome to see more focus on printing cores for laminates rather than tooling. In many cases, the core can also be the tooling. Are there efforts in both lattice, macrocellular structures like honeycomb and foam, and such as microcellular cores?
Oh, absolutely. So I wasn't able to show it because of the length of the presentation, but a perfect example is a wind turbine blade where the core was printed out. And one of the nice parts is you can fill in your hexagonal cell structure to what geometries you want and really look at the design for rigidity where you need it. What's nice about that is it becomes a leave-in tool, and I know I'm using tool again, but as you produce this. So you can imagine in the case for this wind turbine blade, we printed that out and then had a clamshell and basically went through and did the composite structure on the outside of that core. There's all types of different methodologies we can go through, whether it's a winding activity at the end with the leave-in additive cell. This is an area we've spent quite a bit of time in, and there's different levels of cellular structures. As I explained, we've been looking at how we go through and put in different ways to modify the density, so porous materials, but then we can also engineer the structures at different lengths as we go about it.
Thank you. So we'll go ahead and stop here. Again, if there's other questions, please go ahead and send them through. We'll go ahead and take our break, and then Francisco will lead us through our next polling question.
Thank you very much.
Thank you.
Thank you. So here is the second question. Which energy conversion sorry, that was removed somehow. Sorry. I guess that was the previous question. Sorry about that. So here is the second question. And why do you want to use composite materials? And in this case, we have 8 different options. I'm not going to read them all to you, but again, you select one of the 8. And again, if you joined recently, please open the chat, and at the very top, you will see the website where you can go and answer this question. Thank you. And we'll take a short break after you are done with answering that. Thank you.
Okay, we have about a minute left before our break ends. So far, it looks like, in terms of why people want to use composite materials, it looks like both needing lighter weight and looking for cheaper methods of fabrication are of interest, followed by needing corrosion resistance, and ultimately, for some, metallics aren't working for them, and then a few people are saying that they can't make a particular standard part or make a particular part because standard machining methods aren't working for them. All right, let's go ahead and proceed to the next speaker. Derek, are you ready to go?
I am, yep. Bernie, can you hear me?
I can hear you. Thank you.
Okay, sounds good. I am going to stop my slides and then share them. One sec. Okay, and let's see. I will, PowerPoint. So can you let me know, Bernie, if that is coming through for what is being presented? Can you see my slide?
We can.
You can. Great. Okay. So I'll start there. My name is Derek Berry, and I am an employee at the National Renewable Energy Laboratory in Colorado. And so today, as you can see on the screen outline, I'm going to just kind of briefly touch on NREL and IACME, and Bill Peters mentioned a bit as well, IACME, and we are one of the founding members along with Oak Ridge and a few others. I will talk about the COMET facility, a composites manufacturing facility here in Colorado, and the research going on there, and then talk about the pivot towards marine energy that we're seeing within the COMET, and finally talk a little bit about testing and validation at scale. All right, so I'll start with with NREL, and specifically at NREL. NREL is headquartered in Golden, Colorado, but the Flatirons campus where I work and where the COMET is located is about 20 miles north, just near Boulder, Colorado. And we do a lot of things at the Flatirons campus, and traditionally wind, although we're expanding that now. Doing a lot of grid integration, energy storage, high fidelity simulation, things like that, but more and more manufacturing. Obviously, a lot of it has been in the wind area, but we're moving more towards MHK, marine hydrokinetics, water power as well, both in manufacturing and testing and validation. And one of the things earlier speakers have mentioned is sustainability. And I want to touch on here that the long-term viability and sustainability of composites is something that's very important to us, looking at both thermoset and thermoplastic resin systems, and I'll get into that a little bit in my presentation. But it's driving a lot of what we do, the circular economy of energy materials here at NREL. And I just wanted to mention IACME as well. Bill had the slide and touched on it as well. IACME is a Manufacturing USA Institute. We've been in existence for about 6 years now, and you can see that it really brought together 5 original states. You can see the Michigan, Indiana, Ohio, Tennessee, and Colorado. And then the organizations within those states leading the different composite manufacturing and materials innovation and research across different application areas such as vehicles, wind power, compressed gas tanks, and things such as that. You know, it's been in existence, like I said, for about 6 years now, and just about $200 million in total investment across from DOE, AMO, from state funding, from industry funds, and university funds. And it's had quite a bit of an outcome. Bill Peters had shown a similar slide with some of the facilities that have really kind of grown up in collaboration with IACME. You can see those on the right-hand side of the slide, including the MDF that Bill talked about. But then upper left-hand corner there is in Colorado, the COMET facility, which is over on the left-hand side of that picture. And so I'll get more into that. IACME, you can see the core organizations there in the middle, but really is the ecosystem is filled out by so many interactions with industry partners. And IACME has generally about 160 members, industry partners, universities, national laboratories, other organizations, but it's really driven by industry and driven by the composites solutions that we're helping to drive forward to commercialization with these industry partners. So I'll move on to the COMET, the Composites Manufacturing Education and Technology Facility here at the NREL campus in Colorado. And really what we did about 5 years ago, IACME, along with the state of Colorado, along with NREL, provided some funding and the resources in order to stand up a facility, about 10,000 square feet of composite manufacturing space. It's in the Quonset hut. You can see in the upper left-hand picture there. We repurposed that Quonset hut, which existed on our campus, and made it into this manufacturing space. And really, it has served as a way to collaborate with industry partners, with university partners, with national labs, all coming together. And our focus has been on the wind industry, specifically wind blades. That's the largest, really, composite component on a wind turbine. However, we have been pivoting somewhat towards other applications as well, and I'll get into that towards the end of my presentation here. One of the things I want to talk about is the ability to develop composites at scale, whether it's from small coupons developing panels and cutting coupons and performing validation and material testing to fill out databases, but then starting to scale that up to thicker panels or subcomponents, small components of wind turbine blades or subsections of blades or other composite structures, and then finally producing full-size wind blades in this case. And when I say full size, I'm talking about 9 meters or 13 meters. It's not what we're producing in the industry. That's 60 meters, 70 meters, 107 meters wind blades. But for research, we actually do really well at this sort of 13-meter blade scale where we can do it for less cost and do it quicker, so we can innovate and research and get innovative materials and ideas out there in industry and commercialize them. So I'll get into that a little bit as well. It is really a place that we are interconnected with industry partners, as I mentioned, and you can see some of them in the bottom right-hand corner. And over the course of the last 5 years, in this case, well over 20 U.S. wind industry partners and other partners as well, and a lot of different molds and tooling that we use in the Comet. And one of them, Bill actually had a picture earlier. Bill Peters is the 13-meter blade mold that was 3D printed at Oak Ridge National Laboratories, and WIDO and AMO, DOE, WIDO and DOE, AMO, as well as TPI Composites and Sandia National Labs, all had a part in that, and we use that now on a daily basis for our research, really, to do. To try out new innovative materials in composite space. And then, you know, it also brings in different university partners. See a lot of them down there on the left-hand side. But bottom line, kind of enabling collaboration, hands-on throughout the supply chain, from material suppliers all the way through wind turbine OEMs or MHK OEMs in this case as well. So I'm going to move on and then talk about some of the research. You know, we have spent quite a bit of time in the past 4 or 5 years looking at new materials for wind turbine blades and other composite structures. And one of those materials that we focus in on is thermoplastic resin systems. And we have made hundreds of thousands of blades in the wind industry, and when I first got in the wind industry in about 1995 for TPI Composites, we were making thousands and thousands of blades with thermoset resin systems, polyester, vinyl ester, epoxies, and that has worked really well over the years for wind turbine blade production and deployment. However, it is very difficult at the end of the life of a wind turbine blade that's made out of a thermoset resin system to recycle that, to reuse or recycle that. And so we have a challenge in front of us, and other speakers have tackled this a little bit earlier today, which is what to do with the existing thermoset resin system blades, but also how do we innovate and design for recyclability of wind turbine blades and MHK structures down the road. And so one of the things we've been looking at is thermoplastic wind turbine blades. Thermoplastics, you know, I have spent my entire life in thermosets, but when people think about thermoplastics, it's sort of, you know, melting down pellets and using that very high temperature. But what we've done is we've partnered up with Arkema, a chemical company, a French chemical company, but they have their U.S. headquarters in King of Prussia here in the United States, and looked at their Ilium resin system, which is a 2-part in situ polymerized thermoplastic system that works very much manufacturing-wise like a thermoset, like we've always used with epoxy. So it has become a drop-in solution for us. And so we've worked with our industry partners and our university partners to develop panels and coupons and do a whole bunch of mechanical properties. We're using this Ilium resin system with some specialized fiberglass from Johns Manville, and show that the material properties and coupon level and then all the way up to a blade level have a good comparison to the 13-meter epoxy blade that we make as well. We partnered with an ACME with Purdue University to do a lot of modeling and simulation to understand how the new material can work on kinetics and flow and viscosity and exotherm and things like that, so that we can understand that this can be a replacement for blades down the road. We work with Vanderbilt University in the slide here, looking at NDI and NDE, non-destructive evaluation, and moving that up in the manufacturing process so we make better blades rather than just checking them later on with different types of non-destructive evaluation. And we also do a lot of techno-economic modeling here in-house on all of our projects to understand when we're developing new innovative systems, you know, the material may cost a little bit more, but maybe it saves some labor hours or cycle time or reduces CapEx or things like that. And ultimately, all of the new materials and manufacturing process that we look at composite-wise within IACME and NREL and with all of our industry partners, in order to be commercialized, has to be cost-effective as well. And so we use that techno-economic model to understand that a little better. You know, we have, over the years, past couple of years, with the developing this new thermoplastic resin system for wind turbine blades, have actually gotten a lot of recognition for this, and recently with an R&D 100 award for this specific technology in wind turbine blades. I'm going to move on a little bit as well and talk quickly about sort of a follow-on project, and that is looking at the thermoplastic thermal welding. So right now, wind turbine blades that are produced across the world, megawatt-sized wind turbine blades, the different composite structures, the high-pressure skin and low-pressure skin and some of the shear webs, are bonded together, assembled using adhesives, an epoxy adhesive or methacrylate adhesive or something like that. And that adhesive is oftentimes the heaviest part of the blade and the most expensive bill of material unit in the blade as well, and can also have some difficulties in quality control and reliability in the field. And so one of the possible advantages if we produce blades using a thermoplastic resin system is that we can look at thermally weld these components together, eliminate that adhesive. So we've done some studies here in the Comet looking at that. You can see some pictures in the upper middle where we have a couple skins of wind turbine blade. The high pressure and low pressure skin came out of a GE 56.9 meter tip mold that we have in the Comet here. And apply heat and pressure and basically be able to fuse these, depolymerize and then repolymerize, fuse these panels together, fuse these sections together, and we have a lot of great success. The challenge here is going to be scaling up. We've done this on a scale, sort of a benchtop scale, or pretty large benchtop scale here, a meter-long cross-section of a blade, both trailing edge and leading edge, but how do we do this for 90-meter blades, 100-meter blades? You know, what's the energy requirement, the logistics, the equipment needed, and the tolerances to be kept for that as well. So this is ongoing research to really scale this up, but it shows promise, and a lot of people in the wind industry understand that if we can achieve this, we can really possibly have better joints in the field that have higher reliability, better quality, and have less cost in the field, and then reduce the cost of energy overall. We also have been looking at thermal forming. So the slide you see up on the screen now is a project we did with Steelhead and Arkema as well in Colorado State University, where we produced a vertical axis wind turbine. But in this case, after producing a straight section, or could be a protruded section as well, with a thermoplastic blade, we can then thermally form those afterwards. And this has a lot of different applications, not only in the wind industry, but other industries as well. And then a couple more projects I'll finish out with in the Comet that we've been looking at. UMass Lowell has been leading, along with GE, TPI Composites, and LM, a cost optimization, a techno-economic model, and also a Delmia full factory simulation to really understand where we can have cost savings in wind blade manufacturing. And we took those models, and then we did some simulations, and then we also got into onto the shop floor as well. And here at the Comet, we're looking at one-step close. Right now, it takes 2 steps to close a wind turbine blade, where you glue or bond in the shear webs, let that cure for about 4 hours with a heated mold, and then bring the top skin over and bond that on. But if we can look at integrating in the shear web, you see here we're doing in the Comet in October of last year, where we are co-infusing the shear web with the skin, the bottom skin in this case, or the low pressure skin, so then we can bring the high pressure skin on in one step and possibly save 4 or 5 hours in cycle time, save labor hours, and save material costs here as well. So we're using this techno-economic model to identify areas in order to bring down the cost of wind blade manufacturing. And then 2 more projects I'll talk about. One is textile carbon fiber, and so Bill Peters had talked about the CFTF at Oak Ridge, and they are been doing a lot of innovative work in producing carbon fibers using textile precursors. And so taking that, and with the pultruder that Bill showed in one of his slides that is located at CFTF, pultruding this textile carbon fiber into what we call spark caps for wind turbine blades, and that's you can see up in the middle of the blade on the right-hand side, the carbon fiber spark cap. That's a 9-meter blade, a pretty small blade, and we wouldn't really use that carbon fiber spark cap here, but for research purposes we did. And so we're really studying the efficacy, the cost, the material properties, and how we can integrate this into wind turbine blades or other composite structures that uses a lower cost but just as effective carbon fiber coming out of Oak Ridge in the blades that we're researching here at NREL and through IACME as well. And then finally, the last project I'll talk about before pivoting to MHK a little bit is automation. This is the one that we've been working on in the past couple of years with GE and LM Wind Power, and it has been great. We've been looking at automation of wind blade manufacturing, in this case, the finishing process, so things like trimming and sanding and grinding and NDI, the inspection techniques. And this has been a really great success, and we're actually moving this into a wind blade factory within the next couple of months to try it out on very large blades that are 60, 70, 80 meters long, whereas in the Comet we do this, our robotic arm and automation research on 9-meter and 13-meter blades. So this is really something that's pretty exciting for us to look at. Automation is another area where composites and especially wind blade manufacturing has kind of lagged behind, and it's quite a hand and labor-intensive type process for the 26 years I've been doing this. And so getting some sort of targeted automation to help us reduce labor costs, increase quality, and reduce overall cost of energy is going to be really important for us. So I'm just kind of finish off talking about two different things. Our pivot towards marine energy and MHK. Like I said, most of what we've done over the past 6 or 7 years with IACME in the past 5 years in the Comet has been focused a lot on wind power. That's been our mission from IACME and from NREL. However, we just completed a project with Verdant Power, and we produced 4 several-meter-long marine hydrokinetic blades. 2 of those blades, we produced 5 of them. 2 of those blades remain here at NREL, and we're doing full-scale structural testing. 3 of those blades have been shipped for Verdant to New York City, and they're going to be deployed in the East River underwater there. And so one of the innovations, we took the original epoxy blade that was that had existed for this system, and we redesigned it with this thermoplastic resin system that we've been kind of using in wind turbine blade manufacturing research over the past 4 or 5 years. And so the blades that we shipped off to Verdant Power were made with the Ilium resin system from Arkema. And we have done some testing and understand that it has improved seawater performance and robustness, and also can reduce the cost of the blade, reduce the embodied energy, and as I mentioned earlier, reduce those cycle times. And one of the things that can reduce is CapEx. We don't need heated molds anymore if we're going to be using this thermoplastic resin system, whereas we do when we use an epoxy that needs to be post-cured, cured, and post-cured. And with the thermoplastic resin system, we can use non-heated molds, which are a fraction of the cost of those heated molds, and also don't need an oven on the other side of the factory to post-cure the material. So, and we're working more and more with WPTO at DOE and our water power team here at NREL to identify many, many more opportunities for material and manufacturing research in the composite area for marine hydrokinetics. And then I'll just finish off. One of the, and hopefully the videos is playing on the screen there in front of you, one of the really advantages we have here, not only can we research and scale up the materials, composite materials and manufacturing methods, but once we get there, and in this case to a 13-meter blade, we can just take it right across the street to our structural test laboratory, put it onto a test stand, whether it be a wind blade like you see here on the screen, or other composite structures and other applications, and perform static tests like you see here. And if I go to the next slide, and again, hopefully the video is coming through, looking at fatigue test, lifetime tests here. So a full suite of full-scale structural testing to validate at scale. It's not just coupons and substructures. It has taken a full blade, and we have an epoxy blade that we had before, and then we use the one you see on the screen is a thermoplastic blade, and at the end of all of our structural testing, understand the apple-to-apple comparison between this at scale and get us that one step closer to commercializing new technology, new composite materials and technology with our industry partners. And that's what's happening today. Our industry partners are now developing this in 60 and 70-meter blades over the course of this year and next year. So that is the end of my presentation. Just wanted to give you an idea of some of the composite work that we're doing, research on materials and manufacturing at the Comet here at NREL in conjunction with IACME as well. And if there's any questions, I can open up to questions. Thank you so much for your time.
Thank you, Derek. Can you hear me?
Yeah, I sure can.
Yes, so you have a question. You have a couple of questions from the audience. The first question is, what testing has been done to show thermoplastics have better performance in seawater? And they're structural, dimensional, and biofouling.
Yeah, so that's great. So I think biofouling is still ahead of us here, and so this is part of my team, Robin Murray and her team have been working on this, and so I will have to find out some of those answers for you. I know the biofouling is something that is ahead of us to do for testing. What we have done is we've done some soaking of the laminates in seawater here at NREL, and then gone ahead and done apples-to-apples comparison on coupon level, not at full scale yet. For the wind turbine blades, and that has shown promise that it has better performance with the seawater soaking than the epoxy counterpart samples that we used on coupon level testing. So that I'd have to get more information for you, and Bernie, I can certainly do that with our water power team at the Comet, and maybe get some data back to you on what we found there.
Thank you. And then the next question from the audience comes from trying to kind of see the similarities and differences between you and Oak Ridge National Laboratories on your composites research. Sure. You know, how do your efforts complement each other, and how do they overlap?
Yeah, sure. Yeah, there's some overlap there, but what we do is we collaborate in a whole lot of different ways. And so, for instance, we have a program we're working together on 3D printing of wind turbine blade structures, core structures. And so Scott Caron, which is one of my colleagues here at NREL, is working with the folks at Oak Ridge. And so a lot of times on DOE projects, we have collaboration that looks at using the different strengths of different laboratories in order to come to better solutions for industry. You know, it's like I mentioned earlier, sometimes we will leverage different outcomes in laboratories. And so, you know, Oak Ridge did a great job of proving out the 3D printing of that 13-meter blade mold, and now we use it for everyday research for us all the time. It's really kind of our key proving blade, the 13-meter blade. You know, IACRI brings us together as well. You know, we've been working with Oak Ridge on recycling, recycling of composite structures, recycling of composite materials, and there's so much capability there, and also here at NREL. And so, and IACRI brought together with ACMA, the an IACRI member, and ACMA project that Oak Ridge and NREL, but a lot of our industry partners, GE and others, were involved in that as well. So although we have some overlapping capabilities, there's enough that we have specialized that are different that when we bring those together, we can really achieve some pretty good outcomes on composite materials.
Okay, and the last question that was just received is, what kind of lightning strike protection systems will be used with thermoplastic blades?
Yeah, it's a great question. With thermoplastic blades specifically, we can probably keep a lot of the same lightning protection systems that we're already employing, which is just some pucks, metallic pucks at the tip of the blade and some at different locations of the blade with a down cable, down conductor that is either copper or aluminum or something like that that transmits the charge down the blade. Where it really gets interesting, though, is we're looking at carbon fiber in blades, and there's a couple of reasons we do that. We do the carbon fiber composites that I showed you, the textile carbon fiber from Oak Ridge, and as we incorporate that carbon fiber into the blade, or as we go down the road of thermal welding, sometimes we'll use a carbon fiber or metallic strip in the joint in order to provide resistance welding. And so that then makes it a little more difficult. We have to kind of redesign that system. And so we're actually going to sort of mesh, kind of Faraday cage type approach, where we install mesh on the surface of the blade skins rather than a down conductor down in the center of the blade. And we've been doing some testing. We had a project with GE and LM Wind Power and GE Renewable Energy, where we developed, designed, built these in the 56.9 meter mold at the Comet, and then shipped it off to a laboratory in Massachusetts, in western Massachusetts, to actually do lightning testing and show that the new system, and it did have pretty good results of showing that we can redirect that lightning through the mesh on the blade rather than down the cable, and that allows us to use carbon fiber or metal mesh in our thermal welding approaches. So, Bernie, I think the answer to the question is there's a lot of thinking to be being done here. Thermoplastics themselves, you don't need necessarily a new lightning protection system, but if you're going to use carbon fiber in the process, you do. Yep.
Awesome. Thank you so much. That was great.
Yeah.
Thank you.
Thank you, Bernie. Yep.
Yeah, we'll have our next speaker go ahead and prepare to sign on. Ramesh, are you online?
Yeah, can you hear me, Bernie?
I can hear you.
Okay, I guess I'm told to click on Quick Start.
Let's go ahead and get your slides up.
And share my desktop. And if I click on, can you see my presentation now?
I see a background.
Okay, well, that didn't work. I did what I was told. Yeah. Okay.
Do you have two monitors by chance?
No, I have only single monitor. Okay.
It might be a permissions thing in Apple. Do we have your presentation?
Yeah, I sent it to Kathleen.
Okay, Kathleen, do you want to pull it up really quick?
Yep, I'm on it.
And we'll have Kathleen share, and she can run your slides.
Okay, that's wonderful. If you can put it also on full screen, Kathleen, that would be fantastic. Okay, in some ways, I'm going to be continuing with Derek's presentation, where you saw a very broad overview of various manufacturing methodologies, even testing. The question I think we still need to address is how do we make sure that the manufactured composite products that we are going to be putting in service for maybe, I don't know, 20 years or more, is going to last? Is it enough to do fatigue testing, or should we in some way optimize the composite and make sure that before we do testing that already it is optimized? So Kathleen, let me go to the next slide. Yeah, this is what I will talk about. I'll focus on the manufacturing defects. It turns out that the composite manufacturing, in our mind, what you do is not going to be without defects. It's not like metals, where we are given a piece of metal, say steel, aluminum, alloy, and its properties, fracture toughness, elastic properties, elasticity, or whatever. That's not how it works in composites. Every manufactured product with every time history that it has gone through is going to be a new product. That is, we need to know what it is, and we cannot just be taking its overall average properties. So we need to focus on what is inside the composite, and in a service environment, how that interior of the composite is going to respond to the harsh environment we are talking about in marine energy. So I'll very quickly talk about what are the manufacturing methods and what's the level of or severity of defects in them. How do we design composite parts that are manufacturing sensitive? That is, they account for the manufacturing history that has been there. I'll give a couple of examples to illustrate what's going on. There's a huge amount of work in this area, mostly in academia, and I've been involved in it for many years. Obviously, this is not that type of conference where we show scientific results, but I'll just give you some sense of what it is that needs to be done and is being done in order to address the long-term or in any environment, even short-term performance of the composites. Next slide, please. So if I start with the sort of conventional methods, there are still many methods that are manual. That is, they have very little or practically no process control, hand layup, spray layup, pre-preg stacking by hand. Automated methods, of course, are progressing tremendously, but even there, we do not yet have a high level of process control, which means that the defects that we get need to be checked. The typical examples of these methods are filament winding, fiber and pre-preg placement, pultrusion. Next slide, please. Molding methods are the most common ones. You've seen examples of RTM, bottom infusion of resin in many different ways, thermoplastic versus thermoset. All of these are still not at the stage that we can know every time what composite we are producing. So there needs to be looked into to see what is the internal structure that came out. Thermoforming is another example of manufacturing technology where we don't have so much control on the process. And additive manufacturing is booming, it's really going faster than we can think. So there we have recognized that one of the major issues is the density distribution, which is not always uniform. How does that impact the performance of the composites? That's the issue. Next slide, please. So I'll run through very quickly some examples, and because this is Sandia's organized workshop, so it's quite appropriate for me to show you results from a Sandia report, or Sandia sponsor report, by Doug Kieran and his colleagues at Wyoming in 2011. I don't believe things have changed all that much. What you see in the top left picture is how manual intervention is there in producing a wind turbine blade. On the right, you see the mold in two parts, and once you close the mold, you need to pray and hope that everything is going fine. Next slide, please. Yeah, here are some pictures taken in the laboratory. You cut up the composite sections, you look under the microscope, and you see voids. To the right, you see RTM-induced voids and lower technology, less cost in the process, more the defects are, generally speaking. And you can see the voids are much bigger than the fibers in the composite. On the left bottom, you see an example of a void trapped in the consolidation process. Even with vacuum, we're not able to draw the void out, and it's between the layers, and it is initiating cracks that are causing debonding of the fibers. Next slide, please. Here again from Sandia report for thick composites, typically for wind turbine applications, but there's also going to be the case for tidal turbine blades. They are going to be relatively thick, which means that they are going to be thermal gradients, and they are going to produce through shrinkage of the polymer waviness. So the left picture that you see is a severe waviness that has already caused delamination before you put that in service. On the right is a example I have taken from Sweden, where they, for the Volvo company, is developing composites for jet engines and such. And there you see those shaded areas showing you that there's a waviness between the layers, although these are more process-controlled examples. Next slide, please. Okay, it's a cross-section of a wind turbine blade, but it's going to be similar for tidal turbine blade. That is, when you have closed the molds, there are going to be adhesive joints in different places, as you see there. In particular, when you have put a thick layer of resin to create the trailing edge joint, really, if you cut open and see, there will be lots of voids. There will be a lot of gaps between the shell and the resin itself. So that's going to cause delamination, as you can probably see in that picture. So let's go to the next slide, please. Yeah, so how do we approach a manufacturing sensitive design? That is a design that already in the stage of dimensioning of the composite structure takes into account what type of internal structure we are going to be getting, what are the defects, and how do we characterize those. So I have developed a three-step process in this design. The first is where you take some observations, and today we can make observations by many different ways, not just optical microscopes, but X-ray tomography, digitize those observations, and from there create through statistical simulation techniques something called a representative volume element. This is sort of a representation in a statistical sense of what is in the interior of a composite, and then quantify that with defect severity measures that I've been developing in the past few years. This quantification then is combined with testing, not physical testing, because it's really not possible to physically test a material in all possible loading combinations. Our testing machines have severe limitations, and they are very expensive. Happily, we have many computational methodologies available to do virtual testing in so many different ways, and then combine all that knowledge that we get from there and use certain criteria to simmer them down into performance information, so to speak. Those performance measures then, or metrics, depending on, is going to be, in a occasionally high load environment, or it's going to be a steady state, long-term loading environment, and so on. And then finally, the defect severity measure in step 1 has to be correlated. If we can do cause effect type of physical modeling, of course, that's the first choice. But many a times today with machine learning, we are trying to create correlations with the help of certain machine learning neural network type of methodologies. Next slide, please. Yeah, here's the big picture, the manufacturing design strategy or vision, if you like. And there are certain steps, so I'm going to take you through this flow chart without getting into too many details. So the step 1 is a product has been manufactured, whether it's a turbine blade or anything else. It has gone through certain process history. That part I'm not going to be talking about here. I'm going to say at the end of that processing, the product that we have in hand that we put into service environment, the interior that I talked about, there are certain descriptors that I describe as real initial material state and evolving material states. That is or current. That is, as you put it in service, the internal material state changes. All of this, the step 3 and 4, these are information things that go into physical modeling, along with all the details of the microstructure that I talked about, and outcomes from this modeling effort, mostly through computational mechanics, performance measures of structure integrity, durability, damage tolerance if there's an impact, for instance. And finally, the cost is really optimized only when we do a trade-off between performance and manufacturing cost. We cannot just be optimizing manufacturing cost by itself as a process cost, but as what it provides of a product that will perform. Next slide, please. Okay, I'll do 2 examples, and it's going to be too technical if I go into details, and I know that time is limited. So there are these populations of the microstructure that you see there that have defects such as fiber non-uniformity in distribution and voids. Next slide, please. Yeah. One of the important characteristics of the internal structure of the composite is how fibers are clustered together. If they are uniformly distributed, they usually provide good response. But if they are clustered, then they are initiators of the first failure, mostly cracks in the interface and in the matrix polymer between the fibers. Next slide, please. So it's like, describing the cooking by just talking about it and then showing the final product. So through a lot of development that we have done, the type of results that we get out from this analysis is how is the failure going to be depending upon the defect severity of the composite structure. So in this graph, you see on the horizontal scale is some defect severity in terms of the mobility of fibers as you are doing processing. On the vertical axis, you see the applied level of loading at which first failure occurs. And then you see in the clustered fiber case, you start failure much earlier than when you had dispersed fibers case. And these are quantitative results that match the experimental data. Let's go to the next slide, please. Yeah, this is, I'm going to not go into detail, but tell you that there's an integrated methodology that starts with observations of micrographs, digitizes them, and puts them in a finite element model, and then using physical modeling that I talked about, predicts where failure will initiate. This particular example is for fiber waviness, where the composite structure is mostly loaded with compressor loading, because that is a very severe situation compared to in tension many a times, because with fiber waviness you start out king bands and failure of fibers and delamination between layers if there's a thick composite, as I was talking about. So at the last image you see in the bottom, there's a comparison of predictions with actual observations. So next slide is going to conclude. Next, please. Yeah. So what I have essentially done in a few minutes is to hopefully give you some compelling arguments as to how we have to be thinking composites, which is different from thinking metals, because here we cannot be just taking composite as a homogenized product, but it has defects, internal structure that has to be accounted for. The stress and failure analysis must incorporate that. The defect severity has to be quantified. It has to be connected to the failure mode. I gave you two examples very quickly, and the manufacturing sensitive design methodology is growing in academia. There are many of us working on it, and the future direction is to make use of the neural networks, machine learning, artificial intelligence, and hopefully there will be a time in a few years where we can virtually design a composite and then physically make it and be sure that it's going to give us the performance that we need. Okay, with that, I thank you.
Thank you, Nash.
Yeah, thank you. Yeah, thank you, Bernie.
That was awesome. I have a couple of questions for you. I guess my first question is kind of going into what you just said about AI information. What do you think would be helpful there in terms of AI and in terms of the imaging? Do images need to get better, or does the AI, or is there something that AI could do to help you with the imaging process in terms of using non-destructive inspection for determining waviness and other things?
Yeah, definitely. A very relevant question, Bernie. There are two things to say. One is that, you know, the old saying when we were doing computational analysis, garbage in, garbage out.
Mm-hmm.
It's sort of similar in machine learning in the sense that the data that you use to train your model, the quality of the data is going to produce a good outcome or output. That output must be validated. Now, it turns out that if you do not use good data, then you need to have several iterations before your validation is within acceptable error. So images, of course, the resolution of the images is, I would say, somewhat important. But what is more important, and this is where I am today discussing with my colleagues who are very much into this, you would know that most people working in artificial intelligence and machine learning are computer science people. They are not mechanical, aerospace, or materials engineers. So they get hung up on how quickly they are getting results, but they do not quite have the understanding of the physics underlying that. So I'm moving the direction of creating a hybrid machine learning methodology where the physics goes hand in hand with what the machine learning techniques can do. So it's not just the quality of the data, but also the physical understanding. So there are something called surrogate models that help out in putting in information of physics into this methodology.
Thank you. Looks like we're getting close to our time, so I'll go ahead and stop there. Let's go ahead and get our next presenter on, Josh Paquette. Josh, are you on? Or can you go ahead and start sharing your slides?
Yeah, can you hear me, Bernie?
I can hear you.
Okay, great. Let me share.
Thank you, Ramesh.
Sorry for the confusion this morning, Bernie. I don't know why I default to Mountain Time. Up. Okay, how does that look?
Perfect.
Okay. Good morning, good afternoon, everyone. Josh Paquette. I am a staff member in the Wind Energy Technologies Department, although I should say that I think I worked on the very first MHK project in the group when that work was still within the Wind Energy Department. So I have a little bit of experience in MHK. I worked on the project with NREL and Verdant to design a new fiberglass blade for the machine. So what I'm going to talk about today is wind blade reliability. So for the past 10 years or so, I've led a project from DOE looking specifically at wind blade reliability, and that's progressed over time. You know, the industry has grown and changed, and so I've also done work on wind turbine blade design, and more recently been involved in the development of the IEC 61400-5 blade design standard. So what I'd like to talk about today is connecting all of these different topic areas, standards, manufacturing, and even operations on the ultimate reliability of wind blades. So first thing I wanted to talk about, this is for a wind blade, but I think it's for every component. And so this is sort of the lifetime of a component, and something worth thinking about, because very often decisions that you make in one of these areas affect something in another area. And so we go from standards to design, to manufacturing, to transportation and assembly, operation, and then more recently in wind, life extension in some cases, and then finally decommissioning. And the way that we approach standards for wind blades is very conventional, I would say, with other industries. The difference for wind blades is that sometimes we don't have high certainty in these distributions that I'm showing here. But basically, we have some set of loads, or some distribution of loads, I should say, and some distribution of material strengths, or you could even say structural strengths. And then we need to put safety factors on those to account for what we think our uncertainties are. So, the first set of safety factors that I won't be talking about are safety factors on our loads. So there is uncertainty in the loads that components face out in the field. Those can come from either basic challenges with understanding the physics of the problem, all the way to different turbines being sited in different microclimates within a wind plant, and things like that. So these are the loads that we look at for wind blades, and I won't go through all of them, but basically a set of gusts and direction changes and things that could happen to the turbine, fatigue, and we even get into transport and assembly and maintenance, and even repair. As I said, we have uncertainties from complex wind plant flows that affect the loads on the turbine. We could have uncertainties from a high number of faults, in our case, excessive emergency stops sometimes, in transport and assembly, and there's many more. These are just a few that I've picked out to talk about. So then on the other side, we have uncertainties in our resistance. And so so then we factor this, and you can see here that in many cases, and when we have a lot more uncertainties on the resistance side. So I think the graph is dimensionally accurate. And so what kinds of analysis do we need to do, and what kind of safety factors do we need to have? So with wind blades, we have ultimate, which is kind of what everyone thinks of in terms of designing for strength of the component, but we also do fatigue, stability, or buckling, and then deflection. And so for each of these, we have to ensure that the design will be able to last for design lifetime. In our case, that's typically 20 years, although it's been getting longer in some cases. And so then we have to go back, we have to look at each individual possible source of uncertainty. And I'm really happy that Dr. Talreja spoke before me because he did an excellent job of covering the details of some of these. But at least in the standard as it exists right now, we look at environmental degradation, temperature effects, manufacturing effects, calculation accuracy, and load characterization. I'd like to focus on the manufacturing effects as pertinent to today's discussion. But we basically stack all of these partial safety factors together and end up with a combined safety factor. And so as we approach standards, it is difficult, as the previous speaker said. You have to really understand the exact details to understand what the impact on strength or fatigue resistance is. And so there's a range of possibilities for each of these different analyses. And you can see they can be quite stark, something from 1 to 4, essentially. And that's dependent on how well you've characterized your material and the loading that it will undergo. And I'll give an example of that. For wind blades, they're bonded together with adhesives. We often have problems with some of the adhesives at what we call the trailing edge or the back of the blade coming apart. And in some cases, that is because the blade was designed for a certain mode of crack growth, something like shearing. And what ends up happening, because of deflections of the cross-sectional shape, we end up with peeling stresses. And so we can end up with a design that is locally inadequate, just based on not doing the correct analysis, or in some cases, some part of a blade failing and then causing problems with another area. But you can see here, you can get quite low safety factors. I would say 1.2. If you're able to really well characterize your structure and your material, it can be quite a bit higher if you don't. In terms of manufacturing effects, and this is going back again to the wind blade design standard. We have a range of possibilities for this exact effect, or this exact partial safety factor, and it can go all the way from something like 1.3, if you're kind of using maybe literature to look up flaw impacts, all the way down to maybe 1 if you've actually fully characterized the effect of a flaw on the strength or fatigue resistance of your material and structure. These look similar to the previous speaker who talked about. I wanted to point out, a few of these are actual real pictures from wind blades. We can have in-plane and out-of-plane waves. We can have porosity. We can have voids, which are sort of a bigger porosity, or maybe a little bit interchangeable in some cases. But all of these have a different impact on strength of fatigue. Some may present themselves very quickly. Some may take a long time to have damage grow from them. And so it's really important, I believe, to do these tests, not just with perfect materials, but with actual materials that you find from your process. As we talked about, or was talked about, we can have different effects from defects, and this is some work we did, or actually I should mention that our partners at Montana State did this, where we looked at developing probability distributions of defects that we would find in wind blade specimens. And so you can see there, chopping up a bunch of wind blades, looking at the fiber angles or waves in distribution to it, we can end up with a representation of what we might see. And so this is something that a manufacturer would want to do to understand their process better, and either be able to design for it, or ideally be able to alter it in some way. And so then from there, you would go on and you would make some specimens that have those flaws. That's not a trivial thing to do, but it can be done. And then you make coupons from those plates that have whatever type of flaw that you want to examine. In this case, an in-plane wave. Do coupon tests, and then also in some cases you may need to do detail or substructure tests at a little bit higher level. And then do many of these tests, understand the effect on, in this case I've shown both ultimate strength and fatigue between, in the first plot is strength as a function of the wave angle, and the second is the effect on fatigue for a flaw. So you can see those differences, and in this case you'd be able to quantify that, and since you've quantified it, use a lower safety factor. I think it's really important, and this isn't really done in wind yet. It's getting better, but to test all the way from the coupon level all the way up to the full blade. And so right now in wind, we do a lot of testing of coupons. We do full blade tests. The part in the middle is more difficult, and that's an area of ongoing research in the wind industry as to how to test those details. I'll talk a bit about inspection. So invariably, flaws are going to make it out in components. You will need to inspect for them. You hopefully can find them in the manufacturing plant, but sometimes you won't. And so then the next step is to understand what flaws can you catch. This is an example of a fairly intensive investigation of how good inspectors at wind plants are at catching flaws. And so you can see a distribution, or the probability of them detecting flaws, and you can combine them together. You can see quite a bit of spread between different inspectors, so that's something that you have to take into account as well. And in this case, we found that an inspector in the wind industry, based on what we did, was able to detect a flaw of about 1.3 inches in diameter. And so then going back to the design part, if you can't catch a flaw smaller than that, then you need to assume that it exists. So then what do you do once it's out in the field? Well, this is also something that I would say is kind of on the horizon for wind, but if you understand that you do have a flaw, you do have some damage, it's not always practical to repair it immediately. And so us and others have looked at different operational strategies whereby you might change the power output or the rating of the machine to slow the damage growth. Now that assumes that you have very good knowledge of what the damage growth actually is, and I think the comment that was made earlier about AI systems, training them to understand a given platform and specific flaws and damage growth rates for those is really important, and that's something that is also going on in the industry. If you find a flaw, you need to decide what to do with it. This is something that was taken from NASA, I believe, but it's a way of defining how severe a flaw is in general, or how critical it is. So you can look at the location of the flaw and also the size of it. And I think this is something also important to keep in mind, going back to the design process. Not all flaws are equal, so the same flaw, the same size, and the location of it can have quite a bit different ultimate effect. Then finally, if you found a flaw and decide you need to repair it, you need to design repairs and you need to verify that those repairs are actually can regain the strength that you originally had. If they can't, then you need to plan for that in your design. This is an example, again, of some work. I hope this is showing for everyone the video, but this is an example of some composite specimens where we took out some material and put a repair patch in, and you can see, obviously, you can see the repair, right? So it's not completely back to normal, but maybe you can get fairly close. And, you know, like I said, I work on wind. I know this is a more focused at marine hydrokinetics, but it's really important to think about how the scale of what you're working on might change. It's an example from wind of the average rotor size, you know, up until now, and then projection. So you can see we've gone from something like a 40-meter diameter rotor up to maybe approaching a 200-meter diameter rotor for like a typical machine installed on land. There's already 200-meter rotors out there. And so the problems that you face, material thicknesses, and even the materials you use might change over time. So you can't necessarily just use the same methods and knowledge you know, throughout this. Sometimes you have to change those. And then I wanted to show, this is a plot of cost trends. So in the wind industry, managed to bring O&M costs down considerably. So this is meant to be a optimistic slide. You can see starting out something like 90 in terms of dollars per kilowatt year, down to maybe 20. So significant decreases in O&M costs as the wind industry has learned to understand their processes and the impact of flaws, get rid of flaws, or at least design for them. And so to wrap up, I wanted to just give a few lessons from wind reliability that I think are important for MHK. First is that I think this has been covered probably several times, but material properties are inseparable from the manufacturing quality. I think that's true in general for all materials, but this is especially true for composites, and especially true for composites that have a high number of human touches. So wind blades are handmade items. There's a lot of people involved in it that are laying material down, walking on it, touching it, things like that. And those all have impacts on the ultimate strength of the material. If you can't inspect for flaws or show through your process analysis that the flaws don't exist, then you need to assume that they're present and design accordingly. Design for manufacture is crucial to improving manufacturing quality. It's very easy to blame manufacturers for quality issues, but you know, at least some of the time, those start with the design, and you know, designers really need to understand the manufacturing process and make designs that are less likely to have problems, or maybe designs that are easier to find problems if they do exist. Ultimate fatigue testing is obviously essential to finding design and manufacturing issues. This is something that happens in the wind industry a lot. A new blade goes on a test stand, and sometimes very quickly a problem is noticed and that's able to be rectified. I think it's really tempting to try to always go towards a higher quality system or a more expensive material or something like that. It's important to remember that renewables are always a cost optimization problem. You know, there's not a a correct material or a manufacturing method or lifetime or something. It's a combination of all of those together to produce the lowest LCOE. And then, as I mentioned before, it's good to be aware of the problem changing. Wind blades went from small, stiff structures of thin laminates dominated by aero loads to very large, flexible blades with thick laminates, increasingly dominated by gravitational loads, increasingly having sectional deformations that were ignored at smaller scales. So always beware of the problem changing. And I think that's it. Thank you.
Thank you, Josh. This is very informative in seeing how going from just the basic properties to the manufacturing, and then seeing how that relates to the reliability. Thanks for sharing that information. Just I guess one quick question for you is with your reliability work, you were showing some autonomous style techniques.
Yeah.
How has that changed or improved, or how's autonomous work supporting your efforts?
Yeah, so I think in the wind industry, autonomous inspection is just in its infancy. We have the drone, aerial drones are very common right now, but they're doing visual inspection. I think the major impact there has been that we're getting a lot more data about wind turbines and wind plants, and being able to start to build those databases that AI systems can work from. And we can understand better, at least experimentally, the damage growth and things like that. Where I think this might start to have even a bigger impact. Our group and others are working on more sophisticated robots. In our case, we've been working on a robotic crawler that can be deployed from a nacelle on a turbine, go down a blade, and do a very detailed inspection with something like ultrasonic sensors. And you may ask, well, why don't you just have a technician go do that? Well, again, I'm going to go back to my second to last point. Renewables are a cost optimization problem, and so it's not really practical cost-wise to have wind turbine blades inspected by a trained technician. So you have to figure out some other way to do that and bring that inspection technology to the blade. The benefit of it is that you can understand exactly what's going on. So say a drone finds a small crack, you can go do a detailed inspection, know exactly what the damage is, under the surface that you can't see, and design a specific repair for that exact damaged spot, and maybe even pre-manufacture it before it goes up.
Thank you. Okay, so we're going to go ahead and stop here for our presentation. We're now going to start entering our breakout session room. This will actually happen automatically, and in each breakout session there will be a whiteboard for participants to provide their information as we start discussing a couple of topics. And in addition to that, there will be 3 rooms. Each room will go over the same topics and then additional topics if other things are, that do come out of it. But one of the 3 areas that we want to discuss are what composites and manufacturing research is needed to help marine energy technology. The second is what needs to be investigated to support prototype development. And the third question is what gaps must be filled before manufacturing can take place. So now you'll go ahead and you'll see a pop-up window, and this will now take you into your basic breakout session.
Scott, I can hear you.
Okay, yeah. I think hopefully they captured that, because we'll check with Ryan. I think it should still be there. Okay, is anyone still on this line? Can anyone hear me?
I can hear you, Scott.
Hey, Scott, I can hear you.
Not sure if we've been transferred into the full group or still in the breakout here.
I guess so, since we're now able to talk to each other.
Ah, Paul, yes. Full session.
Yeah, it didn't go, but I guess we could have probably talked for a little bit longer.
Yeah, a couple of hours perhaps.
Yeah. We get into some deep discussions, I'm sure.
Hey, Scott, good to hear you.
Hi, Josh, how are you doing?
All right, it's been a long time.
Yeah, it has. Hopefully everything's going good in Albuquerque.
Yeah, I started working back in the office last week. Big accomplishment.
That it is really nice to get back in the office.
Hello.
Hello.
So room 1 is back. Do we have room 2?
I believe George's room, yes, I think we're back.
Do we have room 3?
We do, Bernie.
Awesome. Okay, let's go in order of room 1, 2, and 3. David, did you get back on? Oh, can you hear me? We can't hear you. I think you're muted.
Okay, well, that's about all that we talked about, so...
Nice try.
Sorry, yeah, okay. We had a good group. I enjoyed the conversations. So kind of on the first couple of questions, I don't have that sheet, so I kind of scribbled some notes here in front of me. So still looking at, where are we at? First questions, what composites research is still needed to help the marine energy, and still ends up being materials and understanding the material properties, characterizations of them for the design use, and just kind of a general theme of what happens, what do you do with the water over time? Is it a damage, how do you know it's going to be damaged, and what properties do you put into your design when you do the design? Moving forward to some of the other comments, non-destructive inspection, both before deployment, or so after manufacturing, and then in a deployed condition, understanding how that damage is evolved and evolving was a technology gap that the group identified. And then for kind of a longer term thing where it may be a place for the national labs to really and research world to help get this into is want to move into a digital twin AI side of validation of the design that it's have the tools in place to understand material degradation, the damage, the corrosion, the structure, to be able to do all of that computationally, but beforehand, so you have a better understanding of what the life cycle of your engineered product is going to be before you deploy it. So lots of great conversations, lots of expertise in across the spectrum. Good conversation that was probably not all captured, but those were some of the comments.
Thank you. Room 2.
All right, if you can hear me.
Yep.
All right, so again, as David, great conversation from the group. Then kind of going through the list of questions. So what composites and manufacturing research is necessary? David, this came out of your group as well. Looking at digital twin design, looking at building tools, software tools for a better design handle on composite manufacturing, perhaps with including some unique characteristics for marine energy. Specifically looking at hybrid designs where you have chemistry changing or localized chemistry changing. And then maybe this hops down to number 3, but the need for a reduction in carbon fiber cost. And I think some of the responses, actually, they bridge a few, but thinking about prototype manufacturing. So the need to build 1 or 2 test articles or devices for deployment, it's really challenging just to make 1 or 2 parts compared to production runs of what we have in other industries of thousands of parts. So enabling prototype manufacturing that enables 1 or 2 parts to be produced at reasonable costs. A few of the other things for research, anti-fouling and sediment, especially like riverine or near-shore applications where sediments might be very detrimental to devices was noted. Reliability studies was noted, and pressure evaluation or pressure tanks for deeper water applications, kind of the lack of facilities to do that kind of testing was something that was discussed. And then, okay, so 2, prototype development, and yeah, thinking about scalability or looking at producing things in a laboratory, a manufacturing facility, to maybe dockside shipyards or other localized places, making sure that the training is in place and the knowledge workforce development to enable new technologies to be scaled and transported to different areas. And let's see, George, what have I missed here?
I think that got it. Yeah, means to automate in order to decrease cost. General need to reduce the cost for carbon fiber, of course. Yeah, a lot of cost concerns that came up.
Yeah.
I think that's it.
Okay.
Back to
good
you,
for
Bernie.
group 2.
Thanks. Okay, group 3.
Yeah, so going to question 1, what composites and manufacturing research is needed to help marine energy? I think one thing we talked about was we need kind of more unified quantification of the most relevant material properties and what standards may be associated with those. Getting kind of really basic is just a good understanding of why we use composites and what specific materials we need. Water power is a very broad industry right now with a lot of different challenges depending on your device architecture. So different architectures may need different materials. Stiffness can be a very big driver in design, and it's really going to be an optimization problem like it was in wind. Francisco gave some good information on composite metal interconnects and the related investigation that's needed for those corrosion issues. And there may even be different challenges between river and ocean environments. And we touched on some glass carbon hybrid laminate issues as well. Question 2, kind of what needs to be invested to support prototype development. Again, kind of in the design phase is better dissemination of material properties and the correct data for inputs to design models. And again, kind of talking about more additive manufacturing stuff, and things like water soluble tooling as well, kind of technology that is out there, but maybe not everyone has a great understanding of at the moment. And then what gaps need to be filled so that manufacturing can take place, question 3. We talked about some fluid structure and direction stuff, CFD to loads, and the development of internal tools or the modification of open source tools to become internal ones. Companies may often outsource structural designs. So we talked about that and how they maybe want to move closer to doing everything in-house and kind of grow their understanding of structural design and maybe the development of those tools as well. And one kind of very quick side discussion is at the end was the repair of these structures. I think Josh mentioned that maybe wind, in the development of wind turbine blades, they're a little bit behind on that, the industry. So, the earlier we can understand repairs of these underwater structures, the better, potentially. Francisco, Josh, Matthew, is there anything I missed there?
I think you covered it. I think the reduction in cost of carbon fiber is important too. But
yes, definitely.
No, I think you did a good job. I just mentioned that on the wind side of things, we do have an ongoing project between C&D and specifically related to reducing carbon fiber costs. So that might be of interest to marine energy as well.
Okay, good. That's great.
Thank you. I guess one last opportunity for the audience. Is there anything else that you feel needs to be highlighted before we end today's session? I'll go ahead and take that as a no, unless somebody was talking and was muted. I'm not sure. Nice. Well, it looks like we're about almost out of time. I really wanted to thank you for spending your time with us these last few weeks to go over the seminars, on the basic work to leading to today's workshop. We were excited to share this information and then also start thinking about, what is needed to help with the manufacturing processes of the composite materials that we're starting to explore and what was the next level of need here. And so I really want to thank you for your time and help. Also to the moderators and everybody who helped and panelists and speakers. Again, thank you for your time and preparation of getting this together. This seminar is getting recorded, so if for those of you who had friends and colleagues who couldn't make it, let them know that there'll be a recording available for us to refer back to. Let's see. Lauren, are you still on by any chance, or did you want to say any last words? I guess I'll go ahead and
Hey, Bernie, she was listed as an attendee. There you go, Lauren.
Okay. All right. Sorry about that. Talking to myself over here. Can you hear me now okay?
I can hear you now. I just wanted to say thank you. I just wanted to see if there was any last words from you or.
Yep. Yeah. So I know we're almost at time, so I'll keep it brief. But I just want to thank you, Bernie, as well as, like you said, the rest of the moderators and speakers, as well as the attendees. You know, we couldn't get all of this good content and all of the thoughts and needs that you've identified are really valuable for helping to shape, you know, our program going forward. And also a quick shout out to the NREL team, Kathleen and Ryan, thank you so much for helping to organize and host and moderate this. It sounds like there were a lot of really good discussions in the breakout sessions and lots for us to kind of digest and think through. So Bernie, correct me if I'm wrong, but some of this will be sort of condensed down for ICOE in 2 weeks. So perfect. So yeah, if that's another plug, I guess, for ICOE, if you weren't already planning to attend, an opportunity to get some, you know, takeaways there as well. But yeah, just reiterate the thanks so much, everyone, for your time and participation.
Yeah, and one last topic is we're still going to explore further information about materials. Be on the lookout for the summer. We'll be going over some potential material strategy work as well. And that's it. Thank you, everybody. Thanks for your time. Have a great day, rest of your day, or night, or depending on what time zone you're on. Thank you. Bye.
Bye, everyone.
Bernie.
Bye.
Thanks, Bernie. Bye.